Hello, my dear NEET warriors. Welcome to the complete NEET 2024 formula revision session based on the current NEET syllabus and pattern. Now, this particular formula revision class, I have designed it in such a way that you can effectively complete the entire physics syllabus. All these formulas and all these hidden tricks, in a small amount of time. And the best part is, you can also put on your headphones, peacefully sleep and listen to these formulas. Mentally, you can revise them as well. It's obviously better to watch it, right? But for revision, you can use headphones, you can, speed up the video in 2x speed also and watch it again and again, because there will be many direct questions in your NEET examination. Right, so let's get started. Make sure you smash the like button now to show your full support for this particular video. And remember one thing, the way in which these formulas will be revised, nobody else has done it on YouTube. So all the best. Let's get started with the formula revision. My name is Captain Shreyas. I am your physics master teacher and I have been training kids for a very long time. And over the past few years, I have produced these amazing ranks and I have sent many kids to the top-notch IITs, NITs, BITS and you name it. And I believe that this particular formula session is going to be a game changer for every student who wants to aim the top-notch college, because this is one of the most crucial session for all of you. So make sure you have smashed the like button, share this session with your friends and also subscribe to the channel for more such updates. Yes, let's get going. Yes, this is going to be helpful for all the students. If you are targeting 90 percentile, 99 percentile, 100 percentile, yes, this is going to be. Now, this is going to be a breakless class. Let's get ready. Let's start with translation, rotation, electromagnetism. These three topics can be related to each other. And we'll revise all the formulas together. Okay, so stay with me, my dear warriors. So stay with me. So starting off with translation. In translation, you have something called as the position. The position is given by x. The position is given by x. In rotation, it is nothing but your angular position. It is angular position. It is given by theta. In electromagnetism, the equivalent term which behaves in a very similar way is charge, is basically your charge, which is q. Position, angular position and charge. Then the change of position is called a displacement. It is basically called as your displacement, my dear warriors, and this displacement is nothing but delta x or delta r. And here you have angular displacement, here you have angular displacement, and that is nothing but your delta theta, which is final minus initial. In charge, change in charge is just nothing but the charge which has flown, the charge which flows, which is nothing but delta q, right? Now when you divide this with time, you get velocity. So here you have velocity, which is nothing but del x by del t. But if you want instantaneous, now this was, remember, average. If you want instantaneous, then it will be just dx by dt. In rotational motion, you have angular velocity, which is omega, which is nothing but delta theta by delta t, but this is average. If you want instantaneous, you differentiate it just with respect to time. Here, that term is basically called as your current, and this current is nothing but your delta q by delta t, if this is an average current. But if it is an instantaneous value of current, it will be just the derivative of the charge with respect to time. How many of you knew charge and position and angular position are very, very similar terms? Yes.
What will be the flow of chapters? This is going to be a mixed flow. That's the most important thing. Lot of people revise the formulas chapter 1, 2, 3. That is the worst way to revise the formulas. Don't do it. Many teachers do not know how to revise the formulas. This is the best way, trust me, where you interlink all the chapters. Now, also remember the next term which is going to come. The next term which is going to come after velocity will be nothing but your, will be nothing but your acceleration, So your average acceleration will be del V by del T, whereas your instantaneous acceleration will be dV by dt, In rotation, you have the term angular acceleration, which is alpha. The average angular acceleration will be del omega by del T, whereas the instantaneous acceleration will be d omega by dt. In electromagnetism, there is no name for it, but it is just nothing but di by dt, which is nothing but rate of change of current. Rate of change of current. That's all. Keep this in mind. Also remember one more thing. You can go from one to the other using this simple mind map from position to velocity to acceleration. If you want to go from position to velocity, you differentiate it. Basically, you find the slope of position versus time, which is nothing but dx by dt. If you go from here to here, you just take the slope of velocity versus time, which is nothing but dv by dt. If you go reverse from acceleration to velocity, then you find the area under acceleration versus time. This gives you your change in velocity by integrating acceleration with time. And if you go from here to here, then you take the area under velocity versus time, which gives you change in the position, which is integral velocity with respect to time. This transformation is very helpful for solving those derivative integration questions, right? Yep. Also remember one more thing. Sometimes it might not be a function of time. It might be a function of some other thing. That's when you use your chain rule, and you can also write specifically your acceleration. This acceleration, which was your dv by dt, you can write it as dv by dx into dx by dt. But wait a minute, dv by dx I can just put it as it is, and dx by dt is nothing but velocity. So acceleration is v dv by dx is also very helpful in certain problems of derivatives and integration. All right, I hope till this point everything is clear. My dear warriors. Moving on to this. I'm trying to relate translation, rotation and electromagnetism, all of them. Here in translation, you have a term called as mass, which is going to measure inertia, that is m. In rotation, you have it as moment of inertia, which is the rotational resistance. The symbol for that is I. The formula is either you use sigma mi square, or if you have to use it for a continuous body, then you use integral r square dm. Right? Everybody remembers this? Awesome. In electromagnetism, the equivalent of this is nothing but inductance. My dear warriors. And the inductance, the symbol is L. This is in kg, this is in kg meter square, this is in Henry. Inductance measures how resistant it is to changes of current. It resists any change or fluctuation of current. So that is in electromagnetism. Then over here, if I talk about your kinetic energy, I'll just put the symbol K of translation, then it will be just half mv square. Whereas over here, the kinetic energy of rotation, what is like mass? It is I. So you will put I. What is like velocity? I just told you over here. What is like velocity? It is angular velocity. So that's why you will see the term over here, it will be omega square. Half I omega square. Same way, the energy stored in an inductor, remember, will be just like moment of inertia or mass. What do you have? L. You have L. What is similar to omega or velocity? It is the current. So that's why you will see the term over here, half Li square. That's why the resemblance. Thank you, Lalit, for allowing me. Love you too all. Thank you so much. Okay, I hope this is very, very clear. Very nice thing. Similarly, here you have momentum. And that momentum P is given by mass into velocity. Here you have angular momentum. Depending on whether, don't get confused with inductance. This is not inductance. This is angular momentum. Just that the symbol is same. That's all. Okay. Depending on whether it is a point mass or a big body, you will use M R cross V formula. Or you can also use, instead of mass into velocity, mass can be replaced with I, V can be replaced with omega. Mass with I and V with omega. This is for a particle. This is for a rigid body. A big body like a sphere or a cube or something like that, which is rotating. If it's a point mass, distance into velocity. Alright, so that is your angular momentum formula. In electromagnetism, that is called as flux. So flux will be just like mass into velocity, I into omega. Here it will be L into I. Velocity, omega, everything similar to current. That is what is the resemblance between these three. Is that clear, my dear warriors? Give me a thumbs up. Shall we go ahead? Isn't it amazing to see their relationships? Many of you, I'm pretty sure, did not know about this. Great. Moving on now. Oops, 1 second. I don't know this. Okay, yes. Moving on now to the next one. And that is, in translation, you have something called as force. This force is mass into acceleration. Isn't that right? In rotation, you have torque. Just like it is mass into acceleration, here it will be moment of inertia into angular acceleration. The net torque, here this is, understand, this is always the net force. This is the net torque is I into alpha. To find any of the torque, just use this formula R cross F. The cross product of the position of the force into the force itself. In electromagnetism, this will not be torque, it will be actually electromotive force, EMF. Yes, that is equivalent of this. And you will somehow try to relate EMF with, look at it, MA, I alpha, just like M or I, we have L. Just like acceleration or alpha, what do we have? Just like acceleration or alpha, what do we have? Di by dt. Yes, we have that. EMF is L times di by dt, the magnitude of it. Do you remember? This was Faraday's law of, where you find the rate of change of flux and passing through an inductor, you get the EMF produced is L times di by dt. What a brilliant resemblance. In all of them. Right. Now, moving on to the next one, my dear students. That is basically, in translation, you have something called as the spring. Right? So the spring force magnitude wise is kx. Spring force is kx, but if you put it in vector form, it is minus. Otherwise, in scalar form, it is just kx. Here I am talking about magnitude, here it is direction. In rotation, you have the term called as torsion. In rotation, you have the term called as torsion, meaning you twist an object, it will try to come back to its original shape and size. So there will be a restoring torque. So the torque will be opposite to the twist, and that constant is the torsional constant. Just like spring constant, this is torsional constant. If you look at it magnitude wise, it is just k into theta. This is without the vector form, it is k into theta. Only when you consider the directions, it will be minus. Now, in electromagnetism, guess what is the equivalent of this? What is equivalent of force? EMF. What is equivalent of force? EMF. Torque equivalent EMF, right? What is equivalent of X? We just saw charge. Okay, so think about it. Instead of force or torque, we should put E or basically voltage, EMF, or you can even put or voltage, or basically in general voltage, right? And instead of X, theta, I can put charge. Oh, wait a minute. I know what it should be. 1 by C. 1 by C. Q is equal to 1 by C. This becomes your capacitance. Capacitance. So what you can see, spring constant is like 1 by C because Q is CV, capacitance into voltage. Do you remember? Do you remember this? How many of you remember this? Very good if you remember this. So capacitance is inverse of spring constant, or spring constant is inverse of capacitance. One and the same thing. In fact, so much so that when you try to find the time period of a linear SHM, of a linear oscillation, which is a SHM, linear oscillation time period, the time period is 2 pi under root mass by spring constant, whereas for rotation, for angular oscillations, the time period is given by 2 pi. Instead of mass, what will come? Moment of inertia will come. Instead of spring constant, what will come? The torsional constant kappa will come. It's not exactly K, it's slightly different. It's kappa, looks like K, that's all. Pronounced as kappa, this is pronounced as K, that's all. Otherwise, don't break your head over the symbol so much. Over here, you have your LC oscillations. You have your LC oscillations, my dear warriors. You have your LC oscillations. So think about it, what will you get? 2 pi. Instead of I or M, what will you get? Instead of M or I, what will you get? You will get you will get inductance. You will basically get inductance. And instead of 1 by K, instead of 1 by kappa, what will you get? C. Because I told kappa K is inverse of C. So C will be inverse of kappa. So that's why 1 by K will be replaced with C. 2 pi root LC. Is that clear, my dear warriors? Everybody with me? Everybody with me? Understood? Clearo? Let me know in the chat box. Note it down. Note it down. Everyone. Yes. Awesome. Great. Now, moving on. After spring, after capacitance, alright, after force, alright, we have seen kinetic energy, we have even seen the momentum. So many relationships are holding true between translation, rotation and electromagnetism. Now, moving on over here, what are the different formulas for, moment of inertia and finding the center of mass? Let's also have a look at that. Let's take different bodies, their center of mass, different bodies and their moment of inertia. Starting off with, a hollow hemisphere. It's a hollow half of the sphere, remember that. So it will be like this. The center of mass is at a distance from the bottom. The center of mass is at a distance from the face, which is, at the center, is at, a distance of r by 2. Is at a distance of basically how much? R by 2. Whereas if you take a solid sphere, that means this is completely full, this is completely full. Then from the base, the distance is 3r by 8. This was r by 2, this is 3r by 8. Very good. Next important formula which you should know is for a hollow cone, hollow cone. So the cone is just having the curved surface area, the base is not there. So from the base, from the center, the distance of the center of mass is h by 3, whereas for a solid cone, that means it's completely full, all these things are full, okay. Then from the base, the center of mass is at a distance of h by 4. Not just that, in fact, there is one more formula which many people do not know, and I am going to give that to you. Many people do not know this. That is for an arc. Meaning, imagine just one wire is bent. They give you problems in JEE Mains where a wire is bent. Where is the center of mass located? Just see the angle by which the wire has been bent. Maybe that angle is theta. The radius of the arc is r. Then the center of mass will be somewhere over here. That distance will be r into sine of theta by 2, the whole thing divided by theta by 2. R sine theta by 2 by theta by 2, where theta has to be in radians only. Don't use a degree. So if it is a semicircular arc, your theta will be pi radian. If it is a quarter circle, then your theta will be pi by 2 radian. That's how you're going to substitute it. That is for an arc. Similarly, you get it for a sector also. So for a sector, something like this, like a slice of a pizza. Look at this. This is the slice of a pizza. This is completely solid. The center of mass will be somewhere over here. If this is r, again this angle is theta. Then the center of mass is given by a very similar formula, r sine theta by 2 divided by theta by 2. But here you put the number 2 by 3. It is slightly lesser than 1. That fraction, that 2 by 3 is less than 1 because it comes slightly closer. My dear warriors. Okay, keep this in mind. Similarly, one more formula which you should know. One more formula for center of mass which you should know, and many people get confused over here. There can be 3 different types of problems. See, if you have 3 point masses m1, m2, m3, their coordinates are given, then their center of mass, let's say the x coordinate of the center of mass will be given by m1x1 plus m2x2 plus m3x3 whole thing divided by m1 plus m2 plus m3. Is that making sense? Similarly, the y coordinate of the center of mass will be m1y1 plus m2y2, like that, upon m1 plus m2 plus m3. This is for point masses. Sometimes what happens, there are 3 points, but there is a laminar sheet. It's basically a sheet. It's basically what? A laminar sheet. It's a laminar sheet. It's a 2D object. Then the center of mass is always at the centroid. That means the x coordinate of the center of mass is x1 plus x2 plus x3 by 3. There is no m1, x1, m2, x2. And similarly, the y coordinate will be y1 plus y2 plus y3 whole thing divided by 3. So don't get confused between these two problems. There is one more kind of question which you might get, and that is if you have 3 rods. These are basically rods. In such case, what you need to understand, each rod might have different mass. This rod might have m1 mass. This rod over here might have m2 mass. This rod over here might have m3 mass. each of their center of mass will be here, here and here. Each of their center of mass will be here, here and here. Use these coordinates. Use the centers of the rods to find the center of mass. So you will assume this like just 3 particles now, and then you will use the same formula as before, where you have this as M1, this as M2 and this as M3. Understood, my dear warriors? You have replaced the rods with point masses, and each of these points are at the midpoints, the centers of the rods. Centers means they are basically midpoints. So everybody knows midpoint formula: x1 plus x2 by 2, x2 plus x3 by 2, x1 plus x3 by 2. Midpoint formula on a straight line. Midpoint formula on the straight line. Yes, definitely. Yep. You can continue even from here. Even if you are joined in a little bit late, you can watch the remaining part later on also. Or if you want, you can catch up at 2x speed. Yes. This session will not help you to get 90. Definitely not. This will help you to get at least 99.9 percentile. Because I am going to cover all the formulas of physics for JEE. Alright. So that's the reason why this will help you for 99.9 percentile, my dear students. Alright. So having talked about center of mass now, I think it's time to move on to moment of inertia. It's time to move on to moment of inertia. Let's start with the first body. The first body is obviously a ring. And for a ring, the moment of inertia is mr square. And the formula is very similar for a hollow cylinder. For a hollow cylinder, when you stretch it, then there is no change at all. That's it. It's exactly the same thing, right? It is mr square only. Similarly, if you have a disk, right, that is completely full like this, the moment of inertia formula is mr square by 2. The disk formula is same as a solid cylinder. Keep this in mind. As a solid cylinder, that means it is completely full. This is completely full. All right, this is a completely full cylinder. The formula is going to be the same, my dear students. Moving on after solid cylinder, ring, hollow cylinder, disc, everything. So what is the next formula that will be needed? One is a hollow sphere, hollow complete sphere. The formula is nothing but 2 by 3 mr square. 2 by 3 mr square. That's a hollow sphere. It's like a shell. Hollow sphere or shell is one and the same thing. Hollow sphere or shell is one and the same thing, my dear warriors. Then what is the next formula? The next formula is for a solid sphere like earth or a cricket ball which is completely solid. That formula is nothing but 2 by 5 mr square. 2 by 5 mr square. Is that right, everyone? Very good. Next important formula that you have is for a rod. So when you have a rod and you are rotating it about this axis, the formula is ml square divided by 12. ml square divided by 12. Keep this in mind. Another important thing regarding moment of inertia that you must know, not needed. Even this is not needed. Is the theorems to find moment of inertia about different axes. First thing called as the parallel axis theorem. For parallel axis theorem, you just have some random body and maybe you have an axis which passes through the center of mass. Then you take any random parallel axis. Which is shifted by a distance of d. Then the moment of inertia about this parallel axis is given by moment of inertia about center of mass. Moment of inertia about center of mass, which is ICM. You add to it the shift square into the mass, m into the shift square. So that will be the moment of inertia about the new parallel axis. That is your parallel axis theorem. That is nothing but your parallel axis theorem. I'll put it over here. Parallel axis theorem. parallel axis theorem. Similarly, you also have the perpendicular axis theorem, but this is only valid for laminar bodies. Remember, parallel axis theorem is valid for all 2D or 3D, both 2-dimensional or 3-dimensional, both. But this one, laminar, means only 2-dimensional. Only 2-dimensional bodies you can use it. And what does the theorem say? If you know the moment of inertia about one axis which is in the plane, and you know the moment of inertia about another axis which is again in the plane, let's say I call this as I1, I call this as I2, then you can find the moment of inertia perpendicular to the plane. That perpendicular axis has a moment of inertia just given by I1 plus I2. This is called as the perpendicular axis theorem. Perpendicular axis theorem. Is that okay, my dear warriors? Very good. Very good. So yes, awesome. Right. So we have found the center of mass for all the important bodies. We have seen also the moment of inertia for all the bodies as well as their respective theorems. There is one more small thing which you should know regarding moment of inertia, and that is moment of inertia is mass of the body into k square, where this is called as the radius of gyration. Radius of gyration. Keep this in mind. When you talk about center of mass, and it so happens that there is a body which is attached to, let's say, another body. So together it becomes one composite body. This is your composite body. Then the total center of mass formula XCOM or YCOM is given by you take one part of the body whose mass is m1, you know where the center of mass of that part is, so that is x1. Then you take the other part of the body, maybe you know the center of mass is here, so that mass is m2, center of mass position is x2. The whole thing divided by m1 plus m2, This is for two bodies joined together, like a T section or L section, or a solid sphere plus a cylinder, or hemisphere plus a cylinder, or body with cavity. Then what you do is you assume the whole body as one mass, and you take out that body which has been placed exactly inside the cavity. You assume another body which is just inside the cavity. I will call it m2. So then the coordinate of the center of mass will be given by that whole body which is there, mass m1. For that whole body, the center of mass will be at x1. Whole thing divided by, again put m1 over here, and then you subtract. Instead of adding, you subtract. So here it will be m2 x2, and here it will be m2. That's it. That's the formula. Instead of plus, it will be minus. Is that right? Everybody understanding this? Shall we go ahead to the next part? Don't worry, even if you have not touched many things, many formulas you are going to learn today, and trust me, even seeing the formulas can prove very helpful, because there will be at least 30% questions which are direct applications of formula. Direct. You check any previous year papers, last 2-3 years, you will see the same trend continuing. Okay, everybody with me? Let's move on now to the next point. So we have done everything till here. Yes, translation, rotation, electromagnetism also we have touched upon all the pointers. Great. We have touched energy also, we have touched force also, we have touched momentum also. Great. So now moving on now to the different bodies and their inductance, and then different bodies and their capacitance also. So let's start with each of their bodies. So first is a parallel plate capacitor. Parallel plate capacitor. So it will look something like this. It will look something like this. Two plates parallel to each other. That's all. That's nothing but a parallel plate capacitor. So the capacitance is given by, for a parallel plate, epsilon naught area divided by D. Epsilon naught area divided by D. If there is some medium in between, then you just multiply by K. Then you just multiply by K, that's all. That K is the dielectric constant of the medium which is present inside. So if you put some medium in between over here, there will be some dielectric constant K over here. That's all. Then you have the cylindrical type. Then you have the cylindrical type of capacitor. Where you have two concentric cylinders, one inside the other. That's it. That makes a cylindrical capacitor. So that cylindrical capacitance is just given by 2 pi epsilon naught divided by log of bigger radius by smaller radius into the height of the cylinder. And again, same thing continues. If there is some medium present here, then you multiply it by the dielectric constant. H is the height of the cylinder. R1 and R2 are the radius, inner and outer radius. Always do big by small. Always do big radius by the small radius. Then moving ahead, let me just duplicate this. All right. If you have a spherical capacitor, so you have one sphere inside and another sphere outside, both are shells, then the capacitance for a spherical type capacitor is given by 4 pi epsilon naught 1 by R1 minus 1 by R2. R1 and R2 are the inner and the outer radii, that's it. And by chance again, if there is some medium which is present in between of them, then I can just say I will multiply it by K, that's all. The last type is an isolated capacitor, where you just have one sphere, nothing else, of certain radius. Even that behaves like a capacitor. That capacitance is 4 pi epsilon naught into R. 4 pi epsilon naught into R. Keep that in mind. Is that okay, my dear warriors? Right. This capacitance also reminds me of one more thing which we can probably add over here in translation, rotation and electromagnetism. You know, in electromagnetism, if I use capacitor and the energy stored inside it, so the energy stored inside a capacitor is given by half Q square by C. Half Q square by C. What is equivalent of capacitance in translation? Remember, it is a spring but the reciprocal of it. C is 1 by K or K is 1 by C. So if I write energy stored in a spring, guess what it will be? Instead of 1 by C, I will have to put K. And instead of charge, what is similar to charge? Charge is similar to position or angular position. So here it will be x square. So that's it. So half K x square. Isn't it fascinating? I just told you right over here that just like you have spring constant or torsional constant, you have 1 by C in electromagnetism. And I also explained at the beginning that just like you have position, you have charge, which is very similar, behaves in very similar manner for the other formulas. In rotation, you have the energy stored inside that torsion, in that torsional spring, that is given by half kappa into theta square. Half kappa into theta square. Keep this in mind. Right? All right. Very good. Moving on now to the next part. Let's see. Where are we? Okay, here. Yeah. In capacitor also, there is one more thing which you should know regarding specifically this parallel type of capacitance, specifically regarding this parallel type of capacitance. So when you have this parallel plate capacitor, okay, between these two plates there will be some electric field. That electric field is given by Q by A epsilon naught. Q by A epsilon naught, where Q is the charge on any one of the plate. Remember, there will be charge like this, Q plus Q and minus Q. So Q by area of the plate by epsilon naught. But at the same time, because these plates are oppositely charged, there will be a force of attraction between them. That force is given by Q square, but there will be a 2 over here, and A epsilon naught. When there is 2 below, there is 2 on the top. Keep that in mind. Yep. Keep this in mind. Very, very important. And remember one thing, if you place another charge in between the plates, then the force on that charge, charge is, let's say, small q, between the plates, this is very different from force between the plates. This is the force on a charge between the plates, is given by the charge into this field, which will give you QQ by A epsilon naught. Remember, there is no 2 over here. This force is different from this force. So it's like placing an electron. What is the force on the electron? The charge of the electron is Q. Electric field is E between the plates. But when you find the force of attraction between the plates, then the force is Q square by 2 epsilon naught. Okay. Now what happens is, sometimes you place dielectrics in between. And then you are asked to find the capacitance of it. So imagine dielectric slabs in parallel plate capacitor, something like this. This is one plate, this is another plate, okay, and you can have multiple slabs in between. There is one slab over here, there is one slab over here, and so on and so forth. There is one more slab here, like that. This is slab number 1, this is slab number 2, this is slab number n. Each of them will have dielectric constant K1, K2, K3, Kn. Now, these slabs will also have some thickness. This will have thickness T1, this will have, or I can just put thickness as D1, D2, D3, D4, like that till Dn. The total gap is D, which is nothing but D1 plus D2, like that till Dn. If there was no dielectric slab, then the formula is very simple. If there is no dielectric slab, then the capacitance is very simple. It is epsilon naught A by D. But the moment there are slabs, this D will not come over here. This D will be now split into many D's. This D will now be split into many D's, something like this. You will put D1 plus D2, like that till Dn, but with a small catch, divide that with K1, K2, K3 everywhere. So this will be by K1, by K2, K3, like that till Kn. This formula is much more easy to remember and much more relatable than remembering that weird formula which is like epsilon naught A and then thickness plus the D minus T into K and all those things. So don't remember that weird formula. This formula is much better. Is that right, everyone? Great. Avinash, trust me, this session is much more better than my previous formula sessions. That is one thing I can assure you, because there are many more things that I have done, and the way the presentation is much better, obviously. So make sure you attend this one. Okay, let's move on now. Let's move on now to the next one coming up on your screen. So we saw everything about capacitance of different types. Now let's move on to inductance. Let's move on to inductance. So specifically when we have just a solenoid, when we just have a simple solenoid, then when you just have a simple solenoid like this, the inductance is given by mu naught into n square, mu naught into n square into area of that cross section into basically what else you have? You will have the length, mu naught n square Al. That's the formula that you will get for inductance. Don't get confused between this L and this L. This is the length, this is inductance, okay? So this is just the length, keep that in mind. This is just nothing but the length of it. Is that clear, my dear warriors? Yes, this will be also useful for JEE 2025. Roshan, don't worry, the physics is not going to change in just a matter of few months, correct? So don't worry. Yeah, this will be definitely going to be useful for all of you. This is definitely going to be useful for all of you. Moving on, if there are concentric solenoids, concentric solenoids, that means you have one big solenoid and inside of it you have another small solenoid like this. Then you don't find the self-inductance, you find the mutual inductance. It will no longer be self-inductance, it will be mutual inductance. That will be very similar looking. It will be mu naught N1 N2 into Al. What is N1 N2? Number of turns per unit length of each of the solenoid. Here remember N1 N2 N, these are turns per unit length. Keep that in mind. What is small n? In general, it is nothing but capital N by L, which is nothing but the total number of turns per unit length. That is the meaning of the symbol small n. Correct. Awesome, awesome. Yes, we are going to come to field everything. Yes, we are going to come for field. Obviously, this will be also useful for CBSE board, NEET, everything, bit side. So, my dear students, don't you think that this formula session will not just be useful for this, but also for EMSAT, but also for BITSAT, but also for SRMJ, for VIT EEE, for any other CUT exam, CBSE exam, everything. Wherever physics is there, it is going to be useful, obviously. So just share it with your friends, and as you're watching this video, make sure you smash the like button. Alright, so that's about solenoid. Now let's go to resistance, capacitance and inductance, and let's compare all of them. We are going to come to field, force, everything, potential energy, all these things we are going to come one by one. Now, for resistance, the formula that we use is rho L by A, and we also say resistance depends on the temperature given by the formula R naught 1 plus alpha delta T, where this is nothing but your coefficient of thermal resistance. Rho is called resistivity, L is the length, A is the area of the cross section. The symbol for the resistance is nothing but this. And we write voltage is equal to I into R. Voltage is nothing but I into R. In capacitance, the symbol for it is this one. And we have already seen the capacitance for different types that I will not repeat again. And capacitance is not dependent on temperature or anything. And we know the formula which relates over here is Q is equal to CV. So one will be positive, one will be negative. Q is equal to CV, V is the voltage between them. In case of inductance, the symbol is this one. If it is a self-inductance, the formula goes like this. The flux is L into I. Whatever flux is generated by the current, that will be proportional to the current. The constant of proportionality is the self-inductance. This is for your self-inductance. But the moment you have mutual inductance, that flux will become M into I. This is for your mutual inductance. Keep this in mind. right? Everybody with me till this point? Everything is clear? Cool. We have already seen the capacitance for different types in the previous slides, right? Parallel plate with dielectrics and all those things. So I'm not going to go back to that again. Now moving ahead over here, just observe carefully. When you have resistors in series, like this, basically we are talking about series resistance, then the total resistance is just simple R1 plus R2 like that till Rn. In capacitors, when you have multiple capacitors in series, then what is the formula, my dear warriors? It is 1 by Cs is 1 by C1 plus 1 by C2 like that till 1 by Cn. In inductors, if one inductor is in series with the other is in series with the next one, then the total inductance in series is just L1 plus L2 plus L3 like that till Ln. So inductors and resistors have very similar behavior. Capacitors is slightly odd, it is exactly opposite. And same thing applies for parallel also. So if you have resistors in parallel, something like this, if you have resistors in parallel like this, and then you have capacitors in parallel like this, and then you have inductors in parallel like this. So resistor wise, the formula is 1 by Rp is 1 by R1 like that till 1 by Rn. For capacitors, you just add them C1 plus C2 plus Cn, and for inductors, again it is reciprocal. So 1 by Lp is 1 by L1 plus like that you do it till 1 by Ln. Now when it is in series, what is same and what is not same? Remember that also. Current is same, voltage is different. For capacitors, charge is same. What is different? Voltage is going to be different. Here, what is same is basically your di by dt is same. Di by dt is your same, and what is different is the voltage. Voltage is again going to be different, or even the current will be same, I can say that. All right. And here in parallel, what is same? Voltage is same, current is different. Here, what will be the case, my dear students? Here again, voltage is same, but charge is different. Charge on it is basically going to be different. Here, you can say again the voltage is just going to be the same. What will be different is di by dt is going to be different. Awesomeness. Yes. Obviously, Alia, I will be teaching for advanced also. Great. Many of you remember this. There is one more thing which I think I need to add, especially for series and parallel. I couldn't make a separate slide for it, and that is for cells in series. And then you have cells in parallel. So when you have cells in series with some internal resistance like this, then the total internal resistance in series is just simple addition of resistors. Simple additions of the internal resistance. This is for the equivalent EMF resistance, internal resistance. So this is your equivalent internal resistance. Similarly, you also have the equivalent EMF. The equivalent EMF in series is simply E1 plus E2 plus like that till En. This is your equivalent EMF of all the things in series. But sometimes there are problems where some of the batteries are oppositely connected, so those polarities will be reversed. So that's why I will put plus minus sign over here. Why is that minus sign there? Only in front of those cells which are oppositely connected. Otherwise, they will just add if they are all in the same direction. Yes. I have also added springs before. I think we had done springs, right? All right, Rocky, we have done springs. Just rewind the session back, you will see springs. Now, for parallel, when you combine all these batteries which are in parallel into one single battery, the equivalent resistance of the internal battery will be just like the parallel resistance, so 1 by R1 plus 1 by R2, like that till 1 by Rn. But for EMF, be careful little bit. EP, equivalent EMF in parallel will be, what you should do, put one big denominator, put E1, then put plus E2, then all these things, like that till En. Okay. What you do now, put a line over here between below each of the EMF. You will put R1, 1 by R1, 1 by R2, 1 by R3, like that 1 by Rn. Same thing do over here, 1 by R1, 1 by R2, 1 by R3, like that till 1 by Rn. So that's the formula. Very easy to remember. E1, E2, E3 you put, then 1 by R1, 1 by R1, 1 by R2, 1 by R2, 1 by R3, 1 by R3, like that. But if one of the batteries is oppositely connected, then you will put a minus sign for that particular battery. That's why that plus minus sign will come. That's why that plus minus sign will come. Okay. If you are talking about, oh, for springs in series and parallel, okay, for that also I will put, okay, got it. So for combination of springs, so springs in series, springs in series, springs in series, springs in parallel. The example of springs in parallel is this one. There is one wall over here, there are multiple springs, possibly 1, 2, 3, how many ever, and there is a block. Then the equivalent spring constant, in parallel is just K1 plus K2, like that till the nth spring, So when springs are in parallel, it behaves like capacitors. Springs are like capacitors, remember? So when they are in parallel, where did it go? Yeah, when they are in parallel, you just add them. So same way, you can just, add them right over there. Okay. Yes. Now, when they are in series, that's when the problem happens. That's when you will use the other formula. So if you have springs like this, which are in series, then 1 by Ks will be 1 by K1 plus 1 by K2, like that till 1 by Kn, Is that clear, my dear students? Is that clear, my dear warriors? One more catch over here. Please remember this diagram, I can clearly see they are in parallel, but lot of students do not know that even this diagram, where one spring is here and a mass is here and one spring is here, even these two are in parallel, not in series. There are some questions in JEE which were asked where one spring was on this side and one spring was on that side. Many people think it is in series. No, actually they are in parallel, because if one compresses, the other extends, both of them push in the same direction. Both of them end up pushing in the same direction. Thank you for pointing it out and letting me know for putting it up for the springs. Anything you find, anything you want to ask me, please feel free to ask, okay, as the session progresses. Great, Rocky. Thank you for pointing it out. Awesomeness. So we have done all kinds of combinations over here, but there is something more which I want to do. Actually, let's see if I have a separate slide for that. No. Without the resistance, I don't need the resistance. Here. I'm going to compare capacitance and inductors. This is something which I will need. So let me just duplicate this. Okay, observe this carefully now. If a capacitor is just connected to the battery, just connected, just connected, just connected. Excuse me. Just connected to the battery. Then that capacitor behaves like a wire. That capacitor behaves like a wire. Keep this in mind. So there could be some internal resistance over here, whatever. There could be some resistance over here, but the capacitor just behaves like a wire. Whereas for an inductor, which is just connected to a battery, all right, it behaves like an open switch. It behaves like an open switch. Very important. There are many questions, especially in match the following or multiple choice, all right, or some good questions are there in JEE mains also, JEE advanced, so it is very important, where the circuit is just on and at t is equal to 0, find the current, find the charges. Those questions, use this. So here you can just replace the capacitor with a simple wire. Here you replace the inductor with an open switch. Here it is basically a closed switch. That is how you convert it. Whereas if you keep that capacitor connected in the circuit for a long time, that means it is in steady state. After a long time in steady state, then you will see that capacitor behaves exactly like this one. That means like an open switch. It behaves like an open switch. It blocks the current. It does not like that current. It will block it. Exactly opposite behavior. And over here too, if you have an inductor which is connected in a circuit, connected to a battery, and you leave it for a long time, after a long time, basically it is in steady state, then that inductor virtually does not resist any changes. Currents are steady. The current will be steady. That means it will behave like a simple wire. Or basically it will be like a closed switch. So it will just behave like a wire. A very, very important analysis, my dear warriors. Is that clear? Yes, we are going to do waves, we are going to do thermodynamics, we are going to do optics, we are going to do everything, even modern physics, everything in this particular lecture. Another important thing which you must know is for RC charging. I know the questions on this are very rare, but maybe in some exam they might probably just ask you. So just for that sake, I am giving it to you over here. The charge which is there on this is a function of time, and that is C into E into 1 minus e to the power minus t by RC, where time constant is basically RC. This is your time constant. Okay, and the graph of this looks somewhat like this. Charge versus time, and this value is basically CE. In inductor, a very similar graph comes for LR growth. Instead of charging, you use the word growth. So again, you have a resistance. Here you have an inductor and you have a battery connected over here. Here, instead of charge, you talk about the current. The current is again a very similar function. It is E by R, 1 minus e to the power minus RT by L. So you will see that again here the time constant The time constant is nothing but L by R. This is your time constant for a LR circuit. The graph is very similar. The graph is very similar. It looks like this, and it reaches a steady value of E by R. It reaches a steady value of E by R. Very important again. Let me also make it for the decay and the instead of growth, you will see it will go down. So this is for RC decay, where you have a capacitor which is already charged and you let it decay. That means the charge will slowly die out with time. The charge will slowly die out with time. That charge will be given as Q into e to the power minus t by RC, where this capital Q is the initial charge, and the graph looks something like this, charge versus time. It looks something like this. It starts from Q. Keep this in mind. And over here, in case of inductors, you just let the current slowly die out. It is LR decay circuit. Here the current will be given by a very similar function. It will be initial current into e to the power minus RT by L. So this is your current. It will look something like this. It starts from I0. Is that okay, my dear warriors? And some special things about these circuits over here. When one time constant is over, it is basically 63% charged, or 63% of the final value, 63% of the final charge of basically CE. Here same thing, if you go to exactly a time value of time constant, here it is 63% of E by R, 63% of the final current. And in case of decay, if you go for one time constant, then it is exactly complementary of 63. What is remaining in 63 if you subtract it from 100? If you subtract it from 100, 37, right? So exactly you will see 37% of that original charge is remaining. And here you will see after one time constant, this is 37% of I0, 37% of the initial current. Yes, very good. Yes, awesome. I'm so glad you're enjoying it, Radhe. Hello, Toshita. Yes. Malesh, nobody is going to ask you till that fourth decimal, second decimal and all that. 37 is enough. Don't go to second, third decimals over there. Cool. Okay. So we have learned capacitors, inductors, resistors. We have compared their combinations, springs, cells, everything in this particular section. All right. So I think it's good time that we move on now to the next part. Yep. We are slowly coming to electromagnetism. Get ready. Super, says Raj. Thank you so much. Hello, Aditya. So when we are talking about gravity, electrostatics and magnetism, the first thing that should come to our mind is force. Then we'll slowly go to field and all the other geometries. Okay, you will see the formulas are going to be very similar. Starting off with Newton's law of gravity. So the force of attraction between two masses, this is m1 and this is m2. The force of attraction between any two masses, which follows Newton's third law, is gm1 m2 by r square. This is nothing but 6.67 into 10 to the power minus 11. Then in electrostatics, you have charge 1 and charge 2. They could attract or repel depending on the sign of the charges. The force of attraction or repulsion magnitude wise is nothing but k q1 q2 divided by r square. These are all inverse square laws. So this k is 9 into 10 to the power 9 in SI units. In magnetism, here you have magnetic poles. Please don't get confused between this mass and this m. these are pole strengths. This over here, they are masses. This is charge. Here, these are poles. Like north pole is plus, south pole is minus. Positive charge is plus, negative charge, electron is minus. Same way, these are polarities of the magnet, north pole and south pole. Yep. So, depending on whether the polarities are north, north, south, south or north, south, the force of attraction or repulsion is very similar. It is mu naught by 4 pi m1 m2 divided by r square. This is nothing but 10 to the power minus 7. Mu naught is 4 pi 10 to the power minus 7. That's a standard value which you must remember. Right? Then moving on to the potential energy between these two masses. It is nothing but minus g m1 m2 divided by r. In case of electrostatics, it is plus k q1 q2 divided by r. In magnetism, that potential energy is given by nothing but mu naught by 4 pi m1 m2 divided by r. m1 m2 divided by r. If you notice the graph of potential energy, it is very interesting for all of them. In case of gravity, it is always negative. It is always negative no matter what you do. Always. But in case of electrostatics, it can be either here or it can be here. If it is on the top, that means either both are positive or both are negative. If it is negative, that means one positive, one negative, because positive into negative is a negative number. So maybe one of them is positive, one of them is negative. That's why it will come below. Same thing over here. If the graph is below, then most likely one is a north pole, one is a south pole. But by chance the graph is on the top, then either both are north pole or both are south poles. Okay, so that's the difference between the graphs of magnetism, electricity and gravity. In gravity, it is always below because masses are always going to be positive. You do not have negative masses that you consider. Keep that in mind. Right? Now moving ahead, let me just, yeah. All right. 1 second. Okay. Yeah. Okay, coming to field and potential in both the things. In case of gravity, the gravitational field is the force per unit mass. Right? This is nothing but your field. In electrostatics, the electric field is given by the electric force per unit charge. In magnetism, the magnetic field B, magnetic field has a symbol B, is the force per unit pole. Similarly, the potential V is that potential energy per unit mass for gravity. Here the potential for, this is the potential for electrostatics. It is potential energy per unit charge, and over here the magnetic potential is just given by the potential energy per unit pole strength. And that's the reason why from this, in general, you get, this is now a general relationship, doesn't just stick to any one of them. This is a very, very general relationship. You will see that the change in the potential energy delta U will be mass into delta V or charge into delta V or pole into delta V. That's what you will see. So you will see it will be nothing but a delta V multiplied by either mass or charge or your pole. whether it is north pole or south pole. It depends on whatever quantity you are looking at. That is change in the potential energy. And this one is always the work done by the external force, but this is negative of the work done by the conservative force, either gravity, electrostatic or magnetism. So that minus work done by that conservative force. Keep this in mind. Many times they might ask you what is the work done by electric force. So if you find delta U, that work you will have to multiply by minus sign, then only you will get the answer. If they ask you how much work is needed to bring the system from this to this stage, then they are asking you what is the work done by external force. If they ask you what is the work done by gravity, then you will be finding W conservative. So that will come with a minus sign which you will have to shift back over here. So be careful while solving those questions. Okay, today we are not doing questions, we are revising formulas. Understand, questions or problem solving sessions, we are having so many of them, but I don't think there are many good formula revision sessions. You search on YouTube, there are very few good formula revision sessions. Okay, where it's just formulas, just concepts, just that graphs, just that theory part, or just those things related to the formula, which are taught in a very, very nice mixed manner. You might see maybe chapter wise, but chapter wise is of no use. Chapter wise is of no use, right? Okay. Now we saw this. Let's see some comparisons between them as well for gravity and electrostatics, and then also electrostatics and magnetism. Now before going there, let me tell you that, one second, let me just create a duplicate of this. Let me just bring it here. A lot of tech going on here for all of you. Let's start finding the field, potential, etc. for different things. Observe now carefully. Starting off with a point mass. At some distance. At this point, what is the gravitational field? The gravitational field is given by Gm by r square. At the same point, if you want to find the gravitational potential, it is minus Gm by r. That's all. In case of electrostatics, we will take a charge q and I will be standing at some distance, and then at that point there will be a electric field which is given by kq divided by r square, and at the same point the electric potential will be given by kq divided by r. Similarly, if I have a magnetic pole, of value m, then at some distance the magnetic field due to that pole will be mu naught by 4 pi m by r square, whereas the magnetic potential will be given by mu naught by 4 pi, which is the constant, m by r. Very similar looking formulas. Right? Very good. Next, what do you have? Next, we have the ring, we have the we have the wires, we have even the spheres and the shells and all of that. So for that, I will take it separately, because you will see ring is there in gravity, in electromagnetism, both, but you will not see a shell for magnetism. You will not see a sphere for magnetism. So you will have to take it up in parts, don't worry. But the most common thing is the ring. So let's talk about the ring over here. So like the ring of the Saturn, if it is there of some mass, ring of Saturn is there of some mass, and you are on the axis of it, here you are taking a charged ring. There is a charged ring over here, something like this maybe. There is a charged ring like this, and has a radius r. This is charge q, and you are finding on that axis the field and the potential. In magnetism, you have a current carrying wire. Here you have a current carrying wire. Okay, so be careful. This is a current carrying wire of some radius r, and on the axis you are trying to find things. So what and all formulas are there? Let's have a look. First of all, for gravity, the gravitational field formula looks something like this: G m x divided by r square plus x square raised to 3 by 2. In electrostatics, the electric field formula looks something like this: K Q x divided by same thing, r square plus x square raised to 3 by 2. In magnetism, you will see that the magnetic field formula will be given by mu naught. Be little careful over here. Be very careful over here. Mu naught. Here you will have current mu naught I, and then you have R divided by, here you have 2 times R square plus X square raised to 3 by 2. It's similar but not same. The 2 is not there in electricity or gravity, but it is there in magnetism. And you can see that R is there, but here R is not there, X is there. So that is the only difference. What is X? X is this distance, that distance on the X axis. This is X. X is the distance on the X axis. Is that clear? Then talking about the potential. At this point, what is the gravitational potential? It is minus Gm divided by, you just have root of r square plus x square. Here the formula looks something like this: V is nothing but Kq divided by just root of r square plus x square. Here you don't have any formula for potential, there is no need of it, so don't worry. Okay, so ring potential formulas for electrostatics and gravity is also done over here. What a beautiful slide. I am loving this slide totally. Isn't it fascinating, my dear warriors? Let's go ahead. Let's take it a little bit further now. Every time. Just create a duplicate and keep. Okay, perfect. The next geometry that we need to see is between electricity and magnetism. We have a straight wire. Well, it is not there in gravity. Okay, so let me just see if I have electrostatics and magnetism. Yes, I have it. So let me take a linear charge. This is nothing but a linear charge. Okay, so let me create a duplicate. Okay, so we have a linear charge. Okay, linear charge. This charge is there over here like this. This charge is there like this, and you are at a distance of r. At this particular point, you want to find the field. Here you have a finite wire which is carrying some current, and at a distance of r, you want to find the magnetic field. Okay, so first things first, what you need to do is always join the endpoints. Mark this as alpha, mark this as beta angle. Always join the endpoint with the point where you want to find the field. Find the angle alpha, find the angle beta. Now my dear students, what happens over here is the electric field formula is given by, observe this carefully, here you will have K, here it is lambda. What is this lambda? This lambda is charge per unit length. What is this lambda? It is charge per unit length. I'll just put it over here. It is nothing but the charge per unit length. That is what is going to come over here. And then you will have divided by r, which is the distance, and here you will have sine alpha plus sine beta. In magnetism also, in magnetism, if current is going like this, then the magnetic field will be inside like that. Then the magnetic field is given by mu naught by 4 pi I by R, mu naught by 4 pi I by R. Okay, if you want, I'll just write it separately over here, and multiplied by same term sine alpha plus sine beta. Sine alpha plus sine beta, same term. But there is one thing in electrostatics which is different, which is not there in magnetism. That is, when you have a wire carrying current, the magnetic field goes in circles. But in electrostatics, my dear students, understand there are two components of the electric field also. So this is Ex, and there is also a Ey component. And that Ey component is very much similar. It's scale lambda by R, but just that instead of sine, it is cos alpha, cos beta with a minus sign. Here there is no Y component. These magnetic field lines are circular. These magnetic field lines are circular field lines. Circular field lines. Did you see the difference? Everyone with me on this? Yup. Very good. Very good. Very good. Now, a very similar, oh my God. Okay. Let me just create a duplicate. Now, a very similar looking formula between electricity and magnetism comes for sheets. This is a sheet of charges. This is a sheet of charges. Here what you have is sigma, which is the charge per unit area. Charge per unit area. And that will give you field in both the directions like this. This is uniform field. Here you will have a sheet of wires carrying current. Many wires which are carrying current. So this is a sheet of wires carrying current, and the symbol over here is generally lambda. That lambda is the current which is there per unit length of the sheet. Per unit length of the sheet. So if you go 1 meter, how many amperes of current is flowing in that? That is basically your lambda. That is basically your lambda. This will also create magnetic field like this and like this. Uniform field. You can see that right over here. Probably like this. I hope you are able to visualize it. The magnetic field lines will go like that. They will go from there, they will come over here, and then again they will go from here and come back over here. So that's how the magnetic field lines look like for a large sheet. They are uniform. This field is given by, for electricity, sigma by 2 epsilon naught. Sigma by 2 epsilon naught. In magnetism, this field, this magnetic field, instead of sigma, you will have lambda. 2 will be there. Instead of epsilon below, you will have mu naught on the top. Instead of epsilon below, you will have mu naught on the top. That's the only difference. Very good. Okay, I hope this is very clear. This is for electrostatics and magnetism. Then there is one more formula. Then there is one more formula between electrostatics. Oh my God, every time. One more formula between electrostatics and magnetism, and that is with regards to energy density. That is with regards to the energy density. Energy density. Energy density. So the energy density in case of electrostatics, is given by half epsilon naught E square. Epsilon naught is permittivity. E is nothing but your electric field. This always tells me how much energy is stored or there per unit volume. In magnetism, that magnetic energy density, so that is how much magnetic energy is there. Magnetic energy is there per unit volume. Instead of epsilon, it will be mu naught below. That's all. Half will be there as it is. So it will be B square by 2 mu naught. Very similar looking formula, half half, electric field, magnetic field. Instead of epsilon, there is mu naught, but that is below. That's the only difference. Yes, yes. I hope this is clear. I hope this is very, very clear. For the ring, what? Where did we go? Oh, yes. Thank you so much. This was R square. Yes, this would be R square. Thank you so much for the ring. Dimensionally, it should satisfy. Correct. Makes sense. Fair enough. Cool. Okay, so we have done this for sheet, both for electrostatics as well as magnetism. Remember, in gravity, you do not have anything. Line charges are there. Current with the straight wire is there in magnetism, not there for gravity. Now, you have in gravity and electrostatics, you have a shell and you have solid sphere, which is not there in magnetism. So, in gravity, if you have a shell, that means there is just a mass over here. It has some radius r. That's it. In electrostatics, again, you have a charged shell. Now, when I say shell, it could be a conducting solid sphere, or it could be even just a shell. Either it is conducting or insulating. Both will work, because for a conductor the charges always come on the periphery, on the outside. So a solid sphere also behaves like a shell, only in electrostatics. So the charges are only there on the outer periphery. That's why the behavior is just like a shell. Here you have two formulas depending on whether you are inside or outside. If you are inside, the field is 0. If you are outside, then the charge behaves like a point charge. So it behaves like kq divided by r square. Same thing over here. The gravitational field will be 0. And then here, if it is inside, and if you are outside, then the formula is, gm divided by r square. In both the cases, the graph looks the same for especially the field. So if I draw the graph of gravitational field or electric field versus r, it will be 0 till it is reaching the surface, and then it will be like this. The change happens abruptly at the surface. Keep that in mind. If you talk about the potential, for gravity or even for electrostatics, formulas are again very, very similar. So, say for example, for electrostatics, if you talk about potential inside, then the potential is constant. It is kq divided by capital R. Remember that capital R here stands for the radius of the shell, not variable. It is shell. Be careful. But when you're outside, then the same thing becomes kq divided by small r. Be very careful. You might overlook that small difference here. Very, very careful. Here, for gravity, it is minus gm, but by capital R when you are inside. Capital R is the radius of the shell, and when you are outside, it behaves like a point mass. So, if one again draws the graph of the potential with respect to the distance, I'm just taking the modulus of potential because for gravity it will be negative. Otherwise, the nature is same. This is modulus of potential. Please mind it. For gravity, or else it would be in the fourth quadrant. So it will be constant. And then abruptly it will change like this after R. So that's the graphical analysis. Is that right, everyone? Clear? Yes. Awesome. Now moving on to solid sphere. Here in electrostatics, it is solid insulating uniform sphere. So that means the charges are there everywhere inside and they are uniformly distributed. Here it's a complete solid mass, so the masses are there everywhere, like Earth, like basically Earth. Now when you talk about field, when it is inside, when you talk about field, when it is inside, the formula is K Q small r divided by capital R cube. That's the change. It is proportional to R. Here also it is G small m small r divided by capital R cube. Outside is the simple formula. Outside is the simple formula. It is just Gm by small r square. It is just going to behave like a point mass. So same thing over here. Outside it is just going to behave like a point charge. So if somebody draws the graph of field versus distance, since it is inside and it is proportional to r, it will be a straight line till r, and after that it is inversely proportional to r square, so it will be a curved line. That is for field. That is for field. But for potential, the formulas are little bit tricky. When you are inside, outside formula is same. It is just going to be like a point charge, so it will be KQ divided by R. When you are inside, it looks something like this. It's going to look this way, KQ divided by, you put 2 over here and then put cube. Because you put 2 and cube, here you put 3 and then you put square. 2 cube, 3 square. Here this will be R, just like over here. Just like over here, this will be R. But this over here again will be R only, but over here you put small r square. 3r square minus small r square. That's the trick. I'll repeat over here for gravity. When it is gravity, always a minus sign, don't forget it. Instead of K, it is G. Instead of charge, it is mass. And this is going to be a big expression. First put 2, then cube. On the top, first put 3, then square. Just like over here, there was r cube. You put r cube here, you put r square here, and 3r square minus small r square. That's the only difference. When you are outside, it just behaves like a point mass, so minus gm by small r. Minus gm by small r. If somebody asks you to draw the graph of the potential, versus r, here we'll take the modulus of potential, because otherwise I know it's just going to be the same thing. The graph looks quadratic in nature till r and then becomes 1 by r. So actually first part is a parabola and the next part is a hyperbola. Why? Look at it. This is a square quadratic equation, that's why parabola. This is 1 by r. 1 by r means it is a hyperbola. So that's how the graph nature only will change. Is that clear? Yes. Very nice. Sir, for electric uniform sphere, KQ by R square, right, and not KQ by capital R square. Oh, that one, yes, this will be small r. Thank you for pointing that out. Yes, this will be small r square. In Josh, I wrote capital R. Yeah, it is small r square. Correct. Right. Cool. Thank you for pointing it out. Yes. True Vision Media, no problem. Even if you are late, you can still catch up. And if there are some of your friends who have still not joined the session, share this session video right now in your Telegram groups, in your WhatsApp groups, Instagram groups. Share this to your boyfriend, girlfriend, anyone, cousin, anyone. Just share it. Okay. Impress them. Tell them, see, Shreyas sir is here. Impress them. Okay. Awesome. So let's move on. Now, gravity, electrostatics, magnetism, some things are again common and different. Again, let's come back over here. Starting off with the field lines and the potential. If you take a mass, here you take basically a charge. And again, the charge can be of two types. Here you can take charge. Here you can again take a charge which is negative. Here magnetism, you always have a north pole and south pole always together. You can never actually isolate the polarities. So no matter what you do, you will always get north pole and south pole together as a whole. You can never isolate them. Now the field lines look like this. For gravity, the gravitational field lines are always inwards. The gravitational field lines are always going to be inwards. It's a negative mass. Keep that in mind. Yep. Very good. And for electrostatics, it's always going to be outwards for positive charge and it is inwards for a negative charge. For magnetism, it never originates or terminates truly. It feels like it originated from north and came to south, feels like, but actually it never ends over there. Actually what happens, it continues over here like this. It never truly stops. It feels as if it started from the north and it terminated at the south, but actually it never stopped. That is the only difference. So they are always in the form of closed loops. Similarly, we can talk about equipotential lines. Here the equipotential lines will look like this, circular, something like that. Here also they will be circular, keep that in mind. Circular equipotential lines. Here the potential lines will look a little bit weird. That is not required, especially in the case of magnetism. But just remember that equipotential lines you generally do not worry about in magnetism, mainly for electrostatics and gravity. Now, some of the properties which are very much similar for both of them or all of them is this one. If the field lines are parallel like this, then it is uniform field. But by chance it is like this, then it is non-uniform field. And wherever they are close, the field is going to be strong. And wherever it is far, the field is going to be weak. Also, you will see that this kind of thing is not possible. This intersection is not possible. Intersection of field lines is not possible. Keep this in mind. Also keep in mind, any field line is always directed from a high potential, always towards a lower potential. Keep this in mind. And finally, always remember, if you have electric field, gravitational field, whatever, if this is your field lines, then your equipotential lines are always going to be perpendicular. Keep this in mind. So equipotential lines are always going to be perpendicular to the field lines. And because we see that the field always goes from high potential to low potential, in fact there is a relationship between them, and that is the field, be it electric field, gravitational field, whatever field, okay, which is, let's say, E, is nothing but dV by dr, but with a minus sign. dV by dr, but just with a minus sign. So minus sign because it always goes from high to low, not from low to high. Because it is dropping, that's why that minus sign comes. So rate of change of potential, negative of it is the field. Very, very important. Yes. The notes you will get it after maybe a day or something, but simultaneously if you are noting it down, that is also okay. You can always take screenshots of this, but it will take some time for me to compile all these notes and send it to you. Don't worry, but I'll send it later on. But just don't depend on the notes. Remember, when you practice by hand, see the session, then only it is useful. Or else people are like, oh, okay, I'll download the PDF.
Sorry, see, it is there in my downloads folder. This PDF is there, that institute's PDF is there, those problems are there, that mock test is there. What is use? If it is there in your folder or just there lying under the table, it's of no use. You have to see it, read it, solve it. Understand that. Okay. Then we saw regarding field over here, gravity and electrostatics. We saw all the geometries, ring, everything is done. Okay. Yes, there are few things which are again needed in over here. Let me just duplicate this. Yes. Now, something which is not there in gravity, but it is there in electricity and magnetism. That is permittivity. Dielectric, permeability, all these things, they are not there in gravitation because gravity does not depend on the medium. So in case of electrostatics, because of the formation of dipoles and all of that, you will get this permittivity and all these things. So my dear students, over here you will see the permittivity of any medium is permittivity of vacuum and multiplied by your K. That's all. Multiplied by your K. That is your basically dielectric constant, or you can just put it as relative permittivity. That's all. In fact, you can do one thing. You can look at it like this. Say for example, if there is vacuum, so in that vacuum, the field is given by 1 by 4 pi epsilon naught Q by R square. But in any medium which is present, it is given by 1 by 4 pi epsilon naught. It divides K times, it becomes K times less as compared to vacuum. It becomes K times less. So whatever was there in vacuum, it becomes K times less. So it will become 1 by 4 pi epsilon naught K Q by R square, which you can also write as 1 by 4 pi epsilon of the medium into Q by R square. From this you get epsilon of the medium is permittivity of vacuum into the dielectric constant. Keep this in mind. In case of magnetism, same thing is there. You have your permeability of the medium is permeability of vacuum into something called as relative permeability. Now, also this relative permeability, which is permeability of the medium upon permeability of the vacuum, is 1 plus X. This is called as susceptibility. Keep this in mind. X is called as your susceptibility. It is there in your magnetic properties. And this X is I by H. This I is also called as your intensity of magnetization. And this H is called as magnetic intensity. And if you ask me what is this I and what is this H, well, this H is nothing but your magnetic field which is applied externally divided by mu naught, and this I is the magnetic field which is induced inside any material upon your mu naught. Magnetic field which is induced upon basically mu naught. Very, very important. Yes. So keep all these formulas in your mind, especially with regards to the materials. There is one more formula in electrostatics where you have a dielectric slab and a charge gets induced on it. So the induced charge formula is also there.
which is the actual charge, into 1 minus 1 by K. So if there was a charge on it, if there was a charge on the dielectric slab, then the induced charge will be Q into 1 minus 1 by K. A very, very important formula again. Okay. So usually the questions on this are very less. So if you want, you can skip it also. But very rarely a question comes on this. Okay. But still, I thought I can just give it to you. Okay. Now, next thing is regarding dipoles. Dipoles is not there in gravity. Please understand that. So in gravity, only few things are there. Gravity with electrostatics. So that part I have already done right over here. Okay. So let me go to, where is it? Yeah. Electrostatics, magnetism for dipoles. So if you talk about dipoles, you will need a negative charge and a positive charge of equal amount separated by a distance of L. This is plus Q, this is minus Q. This is a magnetic dipole, basically nothing but also called as a bar magnet. Bar magnet, you need a south pole which is separated by distance of L with a north pole. So this becomes your bar magnet. This is minus M, this is plus M. Then it creates a dipole moment here, that is P. Here it is capital M, that is your dipole moment. So the dipole moment always is from minus to plus, minus to plus. Many people make a mistake there and they put it from plus to minus. You will get less marks. You will get less marks. Yep. So what is the dipole moment formula? It is charge into length. This charge into length. Here in magnetism, it is nothing but magnetic pole into the length. Magnetic pole into the length. In fact, it can also be related to a bar magnet can be made using soft iron and magnetizing it, or you make an electromagnet, meaning you take a coil of some N turns, and that also develops polarities north and south when you pass current through it. When you pass current in a coil, it becomes an electromagnet, and you will see it will also have its own magnetic moment just like this bar magnet, and that is given by number of turns into the current through that coil into the area of the cross section. So NIA. So that is a magnetic dipole moment of a coil which is carrying current. Keep this in mind. Right? Now talking about the field formulas on the axis and all of that, let's have a look. So if you have a dipole, if you have an electric dipole like this, this is a magnetic dipole. Remember, this is south pole, this is north pole. Here this is minus, this is plus. Then you go to any random point. At a distance r, making angle theta. You will get the value of the electric field. Here you will get the value of the magnetic field, and that will make an angle alpha. With the line joining the center and that point. What is that value? That value is given by, you will have K in case of electrostatics, you will have P, and divided by R cube, Kp by R cube. Here you will have 3 cos square theta plus 1. In magnetism, the magnetic field is given by mu naught by 4 pi, capital M. Here you have R cube, please note it, and here you will have 3 cos square theta plus 1. In fact, you can also write the value of alpha. In fact, that is tan alpha is tan of theta, the whole thing by 2, not tan theta by 2. Here also, tan of alpha is tan of theta whole thing divided by 2. That's how you can find alpha. In fact, it so happens that if you are on the axis, this is also called as the axis. This is also called as the axis. If you are on the axis of the dipole, versus the equator. Equator is over here. Equator is here. Look at this. From positive charge, the field lines will go like this. From positive charge, the field lines will go like this. This is basically your equator. This is basically your equator. So from the North Pole, the field lines go like this on the equator. On the equator. This is your equator. You will see that the field on the equator is always the actual field by 2. On the axis it is double, on the equator it is half. You will see why that happens is because the field lines are very close here and then they spread, so it becomes weak here on the equator, so that's why it is half. Bear that in mind, very important. Okay, and how do you get the formulas for axis and equator? Just substitute the value of theta. When you are on the axis, then remember your theta will be 0. When you are on the equator, then theta will be either plus or minus 90 degree. Here, if you are on the axis, theta is 180 degrees. That's how you get it for the axis or for the equator. Okay. Similarly, you have for the potential also. At this point there will be some potential. The potential formula is K P cos theta, but instead of R it is R square. Here the magnetic potential formula is mu naught by 4 pi m by r square. And in both the scenarios you will see that the magnetic potential on the equator is always going to be 0. Whether it is this problem or that problem, always the magnetic potential on the equator is 0, because on the equator theta is 90, so cos 90 will be 0. That's why the potential becomes 0. Is that okay? Yes. Will they give the value of theta? Yes. On the diagram, probably it will be marked. They will show a diagram. One charge here, one charge here. They will show, find the potential at this coordinate or at this point, making angle this much. Something like that. Or they might just give the question, find it on the axis, find it on the equator. If it is axis, you know theta is 0 or 180. If it is equator, you know it is plus or minus 90 degree. Always find the modulus value. Even if you get a minus answer, put it as modulus for field. Okay. For potential, it can be plus or minus. Okay. Okay. Very good. All right. Moving on. Now to the next point, that is dipole inside a field. Observe this carefully now. So if you take an electric dipole or a magnetic dipole and you place it in a electric field or a magnetic field, then there will be a torque on it. The torque will always try to align it in the direction of the field. That torque is P cross E. Same thing over here. That torque will be nothing but magnetic moment cross B. Very, very important. Also, there is potential energy associated with it. So that potential energy is minus m dot B. Here, sorry, not m dot B. It is minus P dot E. Here the potential energy is minus m dot B. That's all. Instead of dipole, it is electric dipole, it is magnetic dipole. Instead of electric field, there is magnetic field. Also keep in mind the three kinds of equilibrium that are there. One is your stable equilibrium. And one is your unstable equilibrium. So in stable equilibrium, what happens? Your dipole is parallel to the electric or the magnetic field. Whereas when it is unstable, you will see that the dipole moment, is anti-parallel, to the electric or the magnetic field. This also you must know. There could be questions on finding the time period and all of that, where you write torque is mb sine theta and sine theta is small, so it is proportional to theta, and that's how you can find the time period of oscillation and all those things. Okay, so there are some questions where oscillations can also be involved in electricity and magnetism, so bear that also in mind. Great. Now, having talked about all these things, I think we have covered almost everything. I don't think we have left anything over here, but in case I remember something, don't worry, I'll come back and again put it up over here. Let's relate all of them now. So if I have force, which is in newtons, okay, generally, right? So if I have force and if I want to go to field, I will divide that force with that charge or that mass or that pole to get the field, correct? Similarly, if I have potential energy, I want to go to potential, I will divide that potential energy with that charge or that mass or that pole, I will divide it. That's how I go to potential. But at the same time, if I go reverse from field to force, I just multiply it. So field into the charge or the mass or the pole gives me the force. Same way over here, the potential difference into the charge or the mass or the pole gives me the potential energy difference. This is how you go from here to here or here to here. Similarly, if you have force and you want to go to potential energy, or potential energy and you want to go to force, say for example you want to go like this, then minus du by dr basically gives you force. Same way over here, minus dv by dr, rate of change of potential, gives you the field. Keep that in mind. And when you go reverse from field to potential, obviously if it was derivative, now it will be integration. So you will get delta V is negative integral of E dot dr. That's what you get. And over here to here, it is again integration. Delta U is minus integration of force dot displacement. That's all. That's how you complete this cycle. It's a very good mind map, I feel. It's a very, very good mind map. Yes. Keep the video as soon as possible, as in cheat codes. Oh, definitely. I'll definitely make a video on that. Definitely. Okay, so that completes that. Now let's go to the laws Slowly we are ending electromagnetism, and I hope you are happy about it. And I hope you have smashed the like button, even if you are watching it recorded. I hope you are, watching it. Even if you're watching it recorded, you're smashing the like button. I want to see the like count going up. Come on, my dear students, put it up. Very good. And call your friends, put it up as your status. You are watching this session. You can tag me also on Instagram, wherever. Great. Yep. Let's go ahead now to Gauss law, Ampere's law, Gauss's law in magnetism, and Faraday's and Lenz's law. So my dear students, over here, Gauss law in electrostatics looks something like this. Cyclic integral or the closed surface integral of electric field with respect to area, which is called as the total flux. This is the total flux of the closed surface, is the total charge which is inside upon epsilon naught. Total charge which is inside upon epsilon naught. That is your Gauss law in electrostatics. In magnetism, if by chance you do closed surface integral of magnetic field with respect to area, this is your magnetic flux for the closed surface, then the answer is always 0. This is because magnetic monopoles, they do not exist. magnetic monopoles that do not exist. Magnetic dipoles exist. Always if there is a positive pole, always there will be a negative pole along with it. That's the reason why the total magnetic charge inside is 0. If there is north, there is south, so always they will cancel out each other. In Ampere's law, what happens? Instead of it's like this law only. Instead of electric field, you will put magnetic field. Instead of area, you will put length. So here you will have cyclic integral magnetic field with respect to the length is equal to, instead of total charge, here it is the total current which is enclosed by the loop upon no. Here you will have into. So total current enclosed multiplied by mu naught. That is the only difference. Wherever epsilon comes below, you will see mu naught will come on the top. That's the only difference. Okay. So this is Ampere's law. So if you want to recollect that also, let me just remind you of that. If you have some wires which probably are carrying some current, something like this, and you take a path like this, you can see there is a path which I am traveling. This is called as an Amperian path. You can take any path, and at every point you find what is the field. And you move some small distance dl, and you keep doing the dot product over the entire loop. The answer is always current enclosed into mu naught. Right? In the case of electrostatics, so current enclosed is only this one, the green ones. This is the current enclosed. The ones in green. The outside currents are never counted. Here also, you might have some positive, negative charges. There might be some charges which are probably outside. Doesn't matter. If you take a surface, this is a closed surface which is also called as a Gaussian surface. All the charges will give the field. All the charges might give some electric field at every point. At each point there might be some small area. If you do the dot product of field with area everywhere, then you will get the answer as this one. That is the meaning of this Gauss law. Correct? I hope you remember. Remember, electric field and magnetic field is not because of inside charges, it's because of inside and outside both. But the integration value is only because of the inside ones. Cool? Okay. Last one, Faraday's law, which is the induced EMF formula. The induced EMF is minus d phi by dt. This induced EMF is always across a loop. So basically, if I go across a loop, EMF means voltage, dV, I add it, so I will get closed surface integral of dV. Closed surface integral of dV, I can also write it as E dot dr, because this is same as integral dV. dV is E dot dr, but yes, there is a minus sign over there that I can put. Okay, I hope you remember this. And this d phi by dt, what I can do, flux I can write it as B dot A, or I can just leave it as it is also. That's also fine. Just keep in mind that this flux is nothing but B dot dA's integration. This is your Faraday's and Lenz's law combined together. Is that right, everyone? Very good. Awesome. So these are all the 4 things together over here. There are few more things which I can put it up for all of you. One is, if you have a solenoid, then inside the solenoid, what is the magnetic field? The magnetic field inside is mu naught, number of turns per unit length, into I. But when you reach the end, then the magnetic field is exactly half mu naught Ni by 2, because the field lines go little bit far away. The field lines actually go little bit far away. So the field becomes slightly weaker. Keep this in mind. And when you have a toroid, toroid is nothing but a solenoid only. It's just that you have bent it. So this is nothing but your toroid. The magnetic field inside this particular toroid is just like the solenoid only. Inside, it is like mu naught. Instead of n, I can also put total turns by 2 pi r. If you are wondering what this r is, this is what r is. The mean radius, the average radius. N is the total turns. N is the basically total turns. Keep this in mind. One more thing. Keep this in mind, that if you are here or here or here or here, you are outside the toroid, the magnetic field outside is always 0. Even in solenoid, if you are here or very far away from the solenoid, the magnetic field outside is negligible. It's almost 0. Keep these things, factors in mind. Hello Shivam. Hello. Yep. What kind of questions they can ask on Lenz's law? Find the direction of the current. Magnet is moving inside a coil. Where will the current be? Always it tries to oppose it. That's all. Those kind of things. Those are the kind of questions. So what are the different laws that you have in electromagnetism? One standard thing, I have already told you this. You have the Coulomb's law. Already we have seen this, right? Which is K, Q1, Q2 by R square, and all those other laws. Gauss law. I have told you that. Ampere's law. Gauss law in magnetism, in electrostatics as well as in magnetism. All these laws are there, right? We have also talked about Faraday's law. Remember, Faraday's law only says that the induced EMF, Faraday's law only says that the induced EMF in a coil, magnitude wise, is just the rate of change of magnetic flux. That's what Faraday said. What did Lenz say? Lenz's law says that the direction of induced EMF or current, always opposes the change in the flux. Keep this in mind. If it tries to increase, the induced current will try to decrease it. If it tries to decrease, the induced current will try to increase the current. It will always oppose it. That is what it is. Again, some more important things. Kirchhoff's current law is also there in electromagnetism. Where you have multiple wires which go in and come out like this. Okay, so the total sum of the currents which are going in is the total sum of the currents which are going out. This is based on the conservation of charge principle. Then you also have the Kirchhoff's voltage law. So if you have certain circuit elements and you're going across a loop, something like this, V1, V2, V3 are the voltage differences across each element, and you come back in that loop, then V1 plus V2 plus V3 plus Vn is always going to be 0. The sum of the voltages across a loop is going to be 0. This is completely based on energy conservation. If you are worried about the signs, sir, I always get confused with the KVL signs. no problem, I'll tell you. Kirchhoff voltage law, sign convention, not an issue at all. So if you have a battery, if you have a resistor with current, this is a battery, right? And finally, if you have a capacitor with some charge on it, if you go from lower to higher, it is plus. Low to high, it is plus. So it is plus E. Current always goes from high to low in case of a resistor. So this will be plus. So this is plus IR. This is lower, this is higher because this is negative, this is positive. So this will be plus charge by capacitance because Q is CV, V is Q by C. Exact opposite if you are going like that. If you go like this, higher terminal to lower terminal, so minus E. Current always goes from high to low. So if you go from this to this, it is minus IR. Positive to negative, you are going from high to low, so it is minus Q by C. So that is the KVL sign convention. Right? Everyone? Cool? Lot of things to learn, right? We are seeing all the laws, whatever were there in electromagnetism. These are the main laws which are, practically there, right? Then, if you go to mechanics, the first thing that you have is your kinematic equations. Remember, kinematic equations are only valid if the acceleration is constant. So V is U plus AT, that's the first equation. S is UT plus half acceleration into T square is the second equation. Then V square is U square plus 2 acceleration dot product with displacement is the third equation. The displacement in the nth second is U bar plus A bar by 2 into 2n minus 1 is the fourth equation. Many people do not know there is a dot product here because in many books and coaching they do not teach this. But there have been questions where in 2 dimension you have to solve the problem, then this dot product is very useful. Otherwise for 1D problems, even if you do not put the dot product, it is perfectly okay. Okay, so this is in mechanics, these are very important, kinematic equations. Obviously you have the Newton's laws as well, that is pretty much standard. So let me also put that up for all of you. So Newton's law of motion. So when you talk about the first law, it is basically the law of inertia, right? Every body stays at rest. It stays at rest if net external unbalanced force, or it stays at rest if the net external unbalanced force is 0, or basically I would say the net external force is balanced. That's a better way of putting it. Net external forces balance each other. If they balance each other, only then it will stay at rest. Then you have your Newton's second law, which is all about that the net external force, if it is unbalanced. First law talks about balanced forces, this is unbalanced. Then it is directly proportional to the rate of change of momentum. After little bit of analysis, that net external force comes out to be the mass of the body into acceleration. But this is only provided if mass is a constant. Otherwise it will not work. The third law is all about action and reaction. So if one force acts on one body because of the other body, then the same force acts on the other body by the first body but in the opposite side. So if I call one of them as the action, the other one will be a reaction. But they will not cancel each other because they are not acting on the same body. Pandu applies on Champa or Champa applies on Pandu. They are two different things. They will not cancel each other. Right? Very good. Also keep in mind this particular concept of pseudo force. If you have a non-inertial frame, that means an accelerated frame, non-inertial frame, which is, let's say, accelerating with A, then if you look at any random object of mass m, then the force acting on it is always opposite, pseudo force acting on it is always opposite to this acceleration. That pseudo force is mass into acceleration of that frame, mass into acceleration of that frame. It is always opposite. So direction wise it's minus, otherwise magnitude wise there is no need to put the minus sign. That was in Newton's law. Then you also have work kinetic energy theorem. You also have the work kinetic energy theorem in work energy chapter, and that theorem says that the total work done by internal plus external forces, is the final kinetic energy minus initial kinetic energy, basically the change of the kinetic energy, Then the next theorem, which is very important, is the law of conservation of mechanical energy. It says that my initial energy, kinetic plus potential, will be final energy plus potential energy only if the work done by non-conservative forces. Which are the examples of non-conservative forces? Like friction, viscous force, drag force. All these forces, they are not doing work. There is no air resistance, no friction. Then the total energy before and after kinetic plus potential will remain conserved. That is your law of conservation of mechanical energy, my dear warriors. Law of conservation of mechanical energy, my dear warriors. Then the next law that you have in mechanics, which is very useful again in many problems, is law of conservation of momentum. And a very similar law is there in rotation, and that is called law of conservation of angular momentum. Very similar, but the criteria is different. When you talk about just linear momentum, then the total initial momentum will be equal to the total final momentum. Only if the net external force is zero. In case of angular momentum, the total initial angular momentum will be the total final angular momentum if the net external torque is zero. So the criteria is different. Instead of force, it becomes torque. Also in conservation of linear momentum, sometimes you might have to use the coefficient of restitution formula, which is given by relative speed of separation after the collision, upon relative speed of approach. This is before, this one is afterwards. Right, this is speed of separation. So this is basically after the collision, and this is always before the collision. If the value of E is basically 1, it is elastic collision. If the value is E0, it is perfectly inelastic collision. Keep this in mind. And if the value of E is somewhere in between 0 and 1, then it is just said to be inelastic collision. Keep these things in mind. Everyone fine till this point? Very good. Awesome.
So many laws in mechanics. Everything is getting revised. Are you having fun, my dear students? Are you enjoying this class? Yes or no? Let me know in the chat box, and smash the like button in case you haven't. Subscribe to the channel. Show some love. Right? Great. Moving on now. Ready? Okay. My God. I also need to stretch a little bit. Continuously I have been teaching, but yes, I am in full josh and full energy thanks to all of you. So let's go ahead. Where were we? Yeah, laws of fluids. Many laws are there again in fluids also. One of the laws is Pascal's law. So Pascal's law is basically any change in pressure gets transmitted everywhere for enclosed incompressible fluid. The most common example is where you will be given two cylinders, one is small, one is big, like this, and yeah, I think one is like this, and they will be connected over here, maybe something like this, and there might be some fluid inside of it. Maybe there is some fluid inside of this, like this, and then they will tell you, listen, there is a force over here, maybe some car or some weight is kept and they are balanced like that. So pressure 1 will be equal to pressure 2. All the pressure changes will be transmitted everywhere. So that's the reason why you will see F1 by A1 will be F2 by A2. So this law is useful in those kind of problems or those kind of questions. You will also see another important law in fluids, that is the law of hydrostatic paradox. Hydrostatic paradox. This is again a very important concept, where no matter what is the shape of your container, no matter whatever is the shape of your container, if they are connected, then you will see that the fluid will fill till the same amount, same height in all these containers. It will fill till the same height in all the containers, irrespective of the shape or the size. So the height is same for all. That happens because of a fact that the pressure at some depth inside a fluid is the external pressure plus rho g h. It only depends on the depth. It does not depend on the lateral displacement or parallel or horizontal displacement. In fact, there is a formula for dP by dH, rate of change of pressure with respect to height. It is minus rho g. This is also called as the pressure gradient. Rate of change of pressure with respect to height, minus because as you go height wise, pressure reduces. As you go deeper, H reduces, pressure increases. That's why the minus sign. So this is the concept of hydrostatic paradox. Then in fluids, the next concept that you have is the Archimedes principle. One of the principle is, if you have some liquid and in that you put up a solid, and let's say it is floating or it is partially submerged or whatever, then the part which is submerged inside, the volume of the solid which is submerged inside is the exact amount of water that is spillover. So if the tub or the bucket was this full, the level of liquid will go up because some part of the solid went inside, so the level of liquid increases.
So that level of increase constitutes the displaced fluid. So that exactly becomes the volume of the displaced fluid, which often is just called as V submerged or V. Then you will experience a upthrust force. This is called as your buoyant force. That buoyant force is exactly this volume, which is submerged into the density of the fluid into G, into your G. That's all. Acceleration due to gravity. Basically, it is just equal to the weight of the fluid displaced. Weight, not volume, weight of the fluid displaced. That is Archimedes' principle. You have many questions on that, where a body is floating and there is some string attached, find a tension in the string, or what is the mass that has to be put so that the body entirely submerges, or a ball is dropped inside, with what acceleration does it go down, or there is probably apparent weight question, all those things. So if there is a question on apparent weight, remember apparent weight is actual weight minus the buoyant force, So you feel lighter on water because your actual weight reduces by the amount of buoyant force, so you will feel as if your weight is less. So that is apparent weight, which is actual weight minus the buoyant force. This is there again in fluids. Then if you go to fluid dynamics, the first thing that you get is continuity equation, law of continuity, and it goes like this. If you have a small area which is becoming big, maybe like that, maybe the liquid is entering here like this, and then it gets spread out over here like this. Here speed is V2, here the speed is V1. Let's say here the area is A1, here the area is A2. First thing you should know is the rate of flow, which is the volume which is going through it per unit time, is just given by a simple formula: velocity multiplied by area of cross section. Continuity says that this rate of flow going in is always the rate of flow which is going out. Therefore, velocity into area, V1 A1, rate of flow going out, which is basically V2 A2. So this is your equation of continuity. What is this? Equation of continuity. Very good. Okay, awesome. Now, after this equation of continuity, most of the times you will need this Bernoulli's equation. You will need Bernoulli's equation or Bernoulli's law. So that says that if you take a standard line and from that you measure the height of the first surface and then you measure the height of the next surface, let's say the pressure at this point is P1, pressure at this point is P2, pressure at that point is P2, then it so happens, using conservation of energy, this is using energy conservation, what you get is this: on this surface, whatever is the pressure, you add it with half rho v square, half rho v1 square, and then you add rho g h1. P1 plus half rho v1 square plus rho g h1 will be equal to P2 plus half rho v2 square plus rho g h2. Same term here, instead of 1 1 1, here it is 2 2 2. That's all. In this, each one of them, please remember, this is work done by external force per unit volume. This one is kinetic energy per unit volume. This one is potential energy per unit volume.
So work done plus kinetic energy plus potential energy per unit volume inside or while going in is also work done plus kinetic energy plus potential energy per unit volume. That is basically using energy conservation. This is what Bernoulli's principle is all about. Is that okay? Very good. And using Bernoulli's principle, what you get is few more things, especially this one over here, Torricelli's law, where you fill a container with some fluid like this, and the liquid comes out like this over here. Till this point, this is your Torricelli's law. Okay, so first thing first, the velocity is given by root of 2g h1, where this one is h1, this is h1. Okay, next, if I call this as this much as h2, then first of all the time to fall is root of 2h by g, but that h is h2. It's like a projectile. It's like a projectile from a hill. Projectile from a hill. Same formula is used. And the range, this one, the range formula is nothing but the horizontal speed, which is v, into the time taken to fall. When you multiply this with this, 2 into 2 will be there, h1 into h2 will be there, g will cancel, it will become 4 h1 h2, which becomes 2 root h1 h2. Keep this in mind. Also, please remember that this range, whatever you get, becomes maximum. This range becomes maximum if h1 equals to h2. That means the hole is exactly in the middle. Hole is exactly where? In the middle. Very good. Keep these things in mind. Then the next law is the law of viscosity. Newton's law of viscosity. So if you have multiple layers of the fluid like this, and you have a sheet, of certain area A, okay, which is having some velocity, like this. So it will experience a resisting force. That is your viscous force. That force is also called as viscous force. That viscous force is given by eta area dV by dH. What is dV by dH? If you see, each layer is going with different velocity. So if you compare from one layer to another layer, there is some extra speed which is there. So there is some extra speed delta V for a difference of delta H. So that is basically rate of change of velocity with height, also called as the velocity gradient. This is also called as velocity gradient. Keep this in mind. That is your Newton's law of viscosity. You also have Stokes' law. In fluids. If you take a ball of certain radius r and let's say it is made to move with a speed v, then you will see that there will be a drag force. Given by 6 pi eta r into v. 6 pi eta r v. Keep this in mind. Using this Stokes' law, you derive the terminal velocity of a falling object. So a body which is just
begin to fall, it increases the velocity, and finally you will see the velocity becomes constant. That constant velocity is the terminal speed given by 2 by 9 r square g sigma minus rho divided by eta. If you are wondering what these terms are, let me explain. This is density of the ball, sigma. Rho is the density of the liquid or the fluid, density of the fluid. This is the concept of your terminal velocity, terminal velocity, which is exactly derived from the Stokes law. So you should know these terms. Many questions do come from here. Yeah. Great. Very good. So that was viscosity law. Then pressure and surface tension. Yes, let's come to that also. Yep. So when we talk about pressure and surface tension, observe this. If you take the free surface of any fluid, the free, which is exposed surface, free surface of any fluid. So understand the fluid is there here. Free surface, and you draw any line anywhere, imaginary line, that is, you take it of length L, you will see that the molecules on this side will pull like this. The molecules on this side will pull the molecules here like this, and the molecules on this side will pull these molecules exactly like this, So that force acting per unit length is called as the surface tension. Surface tension, keep this in mind, surface tension. And you get these kind of problems where you have a wire frame and you have a movable rod, and then there is a film over here. A film always has two surfaces, please bear that in mind. Surface tension is that property where, you know, the surface contracts. The surface has a tendency to what? Has a tendency to contract. Keep this in mind. Has a tendency to contract. So because of this, the tendency to contract, the rod also comes over here. So 100% there is a force on the rod, but that force, do not say it is S into L. Lot of people write it S into L. Since there are two surfaces, my hand has this surface and at the back also there is a surface. That's why you will put 2SL. Okay? Be careful. Lastly, over here, you will also have the surface energy formula. The surface energy formula. Okay? Many people these days goes to US. So USA, United States of America. Energy is surface tension into area. A is the area which is exposed. S is the surface tension. U is the surface energy. Very simple formula. This can be also used where bubbles combine together and question is how much heat energy is liberated. So you know the final area, initial area, subtract it, change in area, multiply by S, you will get the energy. These questions are very common where a drop breaks into multiple drops or many drops combine into single drop. Those kind of questions, right? So that is also very important. Then here in that surface tension part, you also have some more laws or some more formulas. Let me just put it up for you. If you have a surface where one side is a fluid and other side is air, then you will see the pressure on the concave side. The pressure on the concave side is always more than the pressure on the convex side. This is the convex side by a factor of 2s by r, where r happens to be the radius of curvature. This is specifically used for drops and a bubble in a fluid. That's where you use it.
Because when you take a drop, one side is liquid, other side is air. Or a bubble in a liquid, when you boil water, you might have seen bubbles. That bubble has one side liquid, one side air. So there you can use this. But there are some questions where you have a film. This is a film. This has two surfaces. This has two surfaces. The liquid is only there in this part. The liquid is only there in this part. Then also, your pressure on the concave side is more than the pressure on the convex side. This is also called as the excess pressure. The pressure difference is 2 times of this. So it will become 4S by R. The best example of this is a bubble in air. Is a bubble in air. These questions are also very, very common. Is that okay? Very good. Then there is one more law which I need to give you. Yes, let me just put it up over here. That is, if you take a capillary is a very small tube. Capillary means a very small tube. So this is capillary. And there is some liquid in which it is dipped. You will see the liquid might either go up or come down depending on the angle of contact. I'll just give you the theory for that also, don't worry. So the height rise or the fall is given by 2 times surface tension cos theta by rho g r. What is r? R is the radius of the capillary. R is radius of that capillary tube. What is this theta? This is angle of contact. So whenever you take any liquid, you can see either the liquid makes an angle like this with the wall of the container, or the liquid might be just flat, or you might see the liquid makes an angle like this. Here, if you notice, theta is less than 90. Here, if you notice, theta is 90. Here, if you notice, theta is more than 90. The example for this is water when poured in a glass tube. The example for this is when you pour mercury in a glass tube. If you have seen thermometer, you will see the surface is convex up. Here, the example is water in a silver container. Very rare to find it, but yeah, you can try it out at home if you have a silver container. So that is the angle of contact which it makes, the surface, free surface of the liquid. So this gives you the height rise or the fall. If it's acute, then it will go up. If it is 90, cos 90 is 0, it will neither go up nor come down. If it is obtuse, then cos will be negative, means it will go down. Is that right? Everyone with me? Very good. Awesome. Thank you so much, Sanya Ram SGR, for all the love from Tamil Nadu, my state where I was born, in Salem. Thank you so much for all the love. Thank you. Great. Laws of thermodynamics. Let's go to that. So starting off with 0th law of thermodynamics. 0th law of thermodynamics. This is very simple. If temperature of body A is equal to the temperature of body B, that means they are in equilibrium, and you also see that body A is in equilibrium with C, then it means B and C both are at the same temperature. They also are in equilibrium. Yes, black caps, we discussed this yesterday, but yeah, since this is a formula revision session, I know some people might just watch this, right? Maybe after 1 year also, and hopefully they find it useful, right? Okay, that is your 0th law. Then you have the first law of thermodynamics. First law of thermodynamics, I had explained this using the example of Pandu and him eating some nice samosa or idli or whatever. So same thing, if you eat something, you develop some calories, there is some calorie that you can use it for doing some work.
So W, and rest of it might get stored in your body. That means change in the internal energy. So that is your first law of thermodynamics. Keep this in mind, right? And I had mentioned this also before. If heat is absorbed, then it is positive. If it expands, then it is work is positive. And if energy increases, then it is positive, delta U is positive. The exact opposite will be negative. If it releases, instead of absorbing, it releases the heat, then it is negative heat. If it contracts, then it is negative work. And if the energy decreases, then it is negative. Keep this in mind. Very good. No, I am not from IIT Madras. I am from NIT Nagpur. I did my BTech in NIT Nagpur a long time back. Yes. And after that, I did my research from IIT Bombay. And after that, I have been teaching. I've been in multiple companies. I have started my own company also a long time back. I've done many things in life. I've been a software engineer, electronics engineer, mechanical engineer, all kinds of things I've done in life. Okay, so I know what the outside world looks like. That's the reason why I guide you guys so well, because I have a lot of contacts in the industry. I know a lot of people at very good positions everywhere. Okay, so that was your first law. Now going ahead over here. Yes, let me do this. Okay. Second law, actually there are two parts of it. Both are the same thing, but you know, it's like saying I gave you 100 rupees or saying you took 100 rupees from me. I gave you 100 rupees or you took 100 rupees from me is the same thing. It's just like active and passive voice. So one is a Kelvin-Planck statement, one is a Clausius statement. Both of them mean the same thing. I'll just tell you what second law says. Imagine that you have a hot body. Okay, you have a hot body, and on the other side you have a cold body or the cold side. Then heat will naturally flow from hot to cold. Heat will naturally try to go from hot to cold. In that process, whatever heat is going out of that heat, maybe some amount of heat you extract and make it to do some work, like which happens in an engine, which happens basically in an engine, petrol engine, diesel engine, steam engine. This is the example of that. Hot side is where the gases burn. You take that heat, and that heat is used to expand, and it pushes the piston in the cylinder. It does work, and that remaining heat comes out. That's why the engine is hot. It is released to the surrounding. This is possible. There is no harm in it. But what is not possible is you taking out all the heat energy and converting it into work. All the heat energy and converting it into work, nothing goes to cold. This is not possible. This is the first statement of your second law of thermodynamics. Similarly, there is exact other statement which goes something like that. Say for example, this is hot, this is hot, this is cold, this is cold. Heat always goes from hot side to the cold side, but does it ever happen that the heat is going from the cold side to the hot side? Does it ever happen that the heat is going from just the cold side to the hot side? I don't think so that can ever happen. I don't think so that can ever happen, right? You will never see heat is going from the cold side to the hot side naturally. This is not possible naturally, but you can do it unnaturally.
How? By doing some work. By doing some work on it. Not work is done, but work is done on it. This is the process of a refrigeration. Refrigeration. How? Understand this. Whatever is there inside your fridge is cold. You want to make it colder. That means you have to suck the heat. But outside is hot. Correct? Inside of the fridge is cold. Outside of the fridge, normal air, it is hot. How do you make that heat from that colder body come outside? You do electrical work which converts into mechanical work. That mechanical work converts into thermodynamic work. It sucks that energy and throws it outside. That's why this works in the case of refrigeration. So this is allowed for refrigeration. This is basically your second law of thermodynamics. Very good. Awesomeness. Right? So these are some of the laws in thermodynamics as well. Then you obviously have some more laws. Let me come to that as well. Law of thermal expansion. You have the laws of thermal expansion. Those are very, very simple looking formulas. Let me just write it down for you. Change in length is original length into alpha delta T. Thermal expansion coefficient for linear expansion. Original length, change in temperature. Change in the area is original area A0. Coefficient of areal expansion into change of temperature. Coefficient of volume expansion is original volume into gamma into delta T. Your beta is 2 times of alpha and gamma is 3 times of alpha. Gamma is volume, volume is 3 dimensions, that's why 3. Beta is for area, 2 dimensions, length into height, meter square, like that, so that's why 2. Also you have this concept of apparent expansion. So change in the volume apparent. If the container is also expanding and the liquid inside it is also expanding, then it is the volume of the liquid into gamma apparent into delta T, where this is gamma of the liquid minus gamma of the container. This is the apparent expansion. Sometimes it happens that the rod or that object is heated, but it is not allowed to expand. So you will see that there will be some kind of thermal stress. Thermal stress which is developed because it is not allowed to expand. So which is force by area. That comes out to be Young's modulus into alpha into delta T. Young's modulus into alpha into delta T. Very, very important with regards to thermal expansion. Then you get laws for calorimetry also. The law of calorimetry. The law of calorimetry. The law of calorimetry. So where inside an isolated box, you have some maybe hot objects, and maybe you also have some cold objects. When they are left, the heat can't go anywhere. It will just exchange with themselves till they attain thermal equilibrium. So I will say that the heat which is lost by hot body will be equal to the heat which is absorbed by the cold body. This happens till they achieve thermal equilibrium. Till they achieve all the temperatures are equal. Thermal equilibrium. Thermal equilibrium. This system is isolated. Isolated system is called as a calorimeter. Isolated system's best example is a calorimeter, which is made of wood, thermocol, wool, so which are all insulating in nature. And often while doing these things, you might have to use these formulas. Let me put it over here. Heat which is absorbed or supplied will be m into s into delta T. This is your specific heat capacity. Specific heat capacity. Example, the specific heat capacity for water
is 1 calorie per gram per degree centigrade. 1 calorie per gram degree centigrade. For phase change, the formula is M into L. This is your latent heat. For example, you should know this. For water to ice, it is 80 calories per gram, and for water to vapor or basically steam, it is 540 calories per gram. Okay, standard things. Very nice. Moving on. Again, few more laws coming up over here. For conductivity in thermodynamics, heat transfer, if you have a rod of length L, area of cross section A, and heat comes in from here, heat goes out from here, the rate of heat flow, also called as the heat current, this heat current dq by dt is K A, difference of the temperature by the length. Delta T is basically the difference of the temperature. Delta T is the temperature difference between both the ends. You can also convert this rod into a resistor. You can call this as the thermal resistance, which has the formula L by Ka, and you can use all the formulas which you have learned in current electricity. Rods in series, rods in parallel, you can use it exactly like that, where the temperature difference will work like the voltage difference, and the current will be replaced by heat current, which is dq by dt. That's all. This current will be just replaced by dq by dt. So just like you used to have V is equal to IR, here you will have, instead of voltage, you will have temperature difference. You will just have temperature difference, and heat current, which is nothing but dq by dt, and here you will have thermal resistance. That's all. This also works. This is like combining current electricity with heat transfer conduction. Very good. Then apart from this, you also have some laws for radiation. Like this one, the Stephen's law and the Wien's law and all of that. So if you have a body, it will emit, and let's say the temperature of the body is T, it will emit radiation. It will emit radiation of different wavelengths. You can see there are different wavelengths over here, but there are certain wavelengths which are there in maximum amount. You can see very few wavelengths are short, very few wavelengths are long, but most of the wavelengths are in a particular range. So if you draw the graph of the number of wavelengths versus the wavelength, the graph looks something like this. You will see a particular lambda is of maximum quantity. That particular lambda is of maximum quantity. That lambda which is present in maximum amount. You can see this wavelength is present in maximum amount. Very small and very large wavelengths are not so much. Into the temperature is a constant. This is called as your Wien's law. Wien's displacement law. Is that okay, my dear students? Keep this in mind. Next important thing which you should know, if the surrounding sends in some radiation, this is incident from the surrounding. The surrounding could be at a temperature Ts. Out of that, not everything will be absorbed. Some part might just go as it is. That means it is just transmitted. It is just going as it is, like from a glass, some light or radiation just goes through it, transparent. A part of it might be absorbed. A part of it might be absorbed also. Part of it might be absorbed also. And in fact, it might so happen that some of it might follow reflection laws and it will also reflect. If you take a mirror, it will reflect. If you take a black body, it will absorb a lot. These three things can happen. That's why we say whatever heat went in, was incident will be the heat which was transmitted plus the heat which was absorbed plus the heat which was reflected. And if you divide each of these quantities with Qi, then what you get on the left hand side is 1. This one is called as the transmission coefficient. This one is called as the absorption coefficient. And the last one is called as the reflection coefficient. This is called as the reflection coefficient. Keep this in mind. A plus T plus R is 1. Not just that, this radiation which is coming out might not be the same for all the bodies in spite of being the same temperature. The reason for that is not all the bodies behave like the ideal body, which is the black body. So you have something called as the emissivity of the body. So emissivity of the body E, is nothing but how much heat is emitted by our body, our normal body, as compared to how much heat is emitted by a black body. That is emissivity. So for a black body, emissivity is 1. For normal bodies, it can be 0.8, 0.7 because it emits lesser than the ideal black body. And then Kirchhoff gave one statement. So there is one statement by Kirchhoff. Let me just put it over maybe here. So according to Kirchhoff's statement, Kirchhoff's law, it so happens this absorption coefficient also equals the emissivity. A very, very important law given by Kirchhoff. A is equal to E. So good emitters are also good absorbers. And bad emitters are also bad absorbers. Black body emissivity is 1. That means it emits the most. So it is a good emitter. So it also absorbs a lot of radiation. Is that okay? So keep all these things in mind. And the last thing that you need to know over here is the final rate at which heat is emitted with respect to time is emissivity, the same emissivity, into sigma A, then T raised to 4. This is the amount of heat emitted. But I'm not interested in just the heat emitted. I'm interested in the net heat which is entering plus which is emitted. So the total net heat which I want to calculate, that will be T raised to 4 minus Ts raised to 4. This is a net heat transfer. dq by dt. Okay, will be E sigma A T raised to 4 minus Ts raised to 4. Keep this in mind. So your entire heat transfer radiation part is almost there on this slide, if you notice, right? Your entire heat transfer is there on this slide. Is that clear, my dear warriors? Oh my God. Yes. Awesome. Great. Okay. So that completes heat transfer. Laws of thermodynamics, that is done. So I don't think I need that slide over here. Going to projectile, few more things are there. Looks like it is going beyond what I expected, guys. So we'll take a break after some time and then we'll again return. This session is going to continue. This session is going to continue for a long time. I thought that this will end by
dinner, but I think I'm explaining everything, so that is a good thing also. So I hope it is okay if I continue even after dinner, after some break. Okay, but right now it's not the break time. Let's just continue with their session. So projectile motion, initial speed u, this is theta. As the ball goes up and down, the acceleration due to gravity is only downwards. Acceleration is not there in the x-axis. Acceleration in the y-axis is there. So that's why velocity in the x-axis remains constant, which equals to u cos theta, But velocity in the y-axis will follow u plus at rule. So it will be uy plus ayt. So you can use it as u sine theta minus gt. That's what you can use in the y-axis. So you will see that this ball, which has some velocity, it will have two components, vx and vy. This x component will always be u cos theta. It will only change in the y direction, where I can write this component as u sine theta. Not just that, this ball will have some coordinates. This is x, this is x and this is y coordinate. That y coordinate is given by x tan theta minus gx square by 2u square cos square theta, which you can also write as x tan theta 1 minus x by r. What is r? R is the range. What is r? R is the range of the projectile from here till here. That is the range of the projectile. You should know all these things. Okay. Yes. Let's move on. Now the formulas: vertical free fall projectile and inclined plane projectile. What about seeing all the formulas at once, right? Isn't it amazing? So you throw a ball up, it goes up like this and comes down over here and comes down over here. The total time of flight is 2u by g. In case of projectile, you throw the ball, it goes like this and falls over here. The total time of flight, very similar to this, 2u by g, but here you will have just sine theta. Inclined projectile, depending on whether it is up or down, the plus and minus sign comes. I'll just give you for up the incline. If it is down the incline, you just will use minus sign. That's all. So this is the inclined plane. This is, let's say, alpha. You throw the projectile like this, it goes and hits over here. This total angle is theta. This angle is alpha. Remember, this total angle is theta. Okay, be careful. If you want, I will mark it in different color also. This total angle is theta. Keep this in mind. Then the time of flight is very similar looking formula. 2u sine theta minus alpha upon g cos alpha. This is the formula for up the incline. If it is down the incline, this minus will become plus. Theta minus alpha will become theta plus alpha. That's all. That's the only difference. Is that okay, everyone? Yes. Then going to the next formula, which is maximum height. The maximum height will be nothing but u square by 2g, where velocity is 0 at the top. At this topmost point, velocity is 0. Here, the maximum height, very similar to this. It will be u square sine square theta by 2g. But velocity is not 0. It is minimum. In fact, it is just u cos theta. Reason being, horizontal velocity will always remain u cos theta. It will never go off. So even at the topmost point, remember this, u cos theta will be 0, but the y component, u cos theta will be there, but the y component will vanish off. That's what it is. And in this case, you generally do not have the height formula, but even if you want to find this height, then you can use very similar looking formula as over here. So that height will be u square sine square theta minus alpha by your 2g. Here you will have your cos alpha by your 2g cos alpha. That's all. That's the only difference. right? Then talking about the range, here there is no range, it falls at the same place, it falls at the same place, so there is no point of talking about the range. Here the range is 2u sine theta cos theta by g, and the range is maximum at 45 degrees. Keep this in mind. Here the range formula looks very similar to this. Observe, it is 2u sine theta minus alpha into cos theta. Sorry, this was 2u square, my bad. Yeah, 2u square sine theta cos theta. Here it is 2u square again, sine theta minus alpha cos theta upon g cos square alpha. That's it. That's the formula for up the incline. If it was down the incline, this will become plus, this will also become plus. That's the only change. Will you be able to do it? Will you be able to do it? Everyone? Okay. Guys, make sure that you do not spam or else the admin will start blocking. Yes, come on. Whatever it is, whosoever started or ended, just forget it. Just concentrate on the class or else the admin will block you guys. Okay, concentrate on the lecture. Okay, let's go to circular motion, then SHM, then AC, transverse waves, everything. Wow, so many things are there. Okay, let's go. Let's go. Ready guys, let's do this. Okay, circular motion. What are the different formulas in circular motion? If this is the velocity, this is the radius, then first formula is V is R omega. This is your tangential velocity is radius times angular velocity, one of the equations. Next important thing which you should know is that as this moves, there might be some tangential acceleration also. There might be some tangential acceleration also. That will be R, instead of omega, it will be angular acceleration. This will be tangential acceleration. Tangential acceleration formula is R into angular acceleration. At the same time, it is changing the direction. So it will also have centripetal acceleration. That will be V square by R, or either use omega square R. That is the acceleration towards the center. So the total acceleration will be the net vector sum of centripetal plus the tangential acceleration. Keep that in mind. Not just that, when there is acceleration, there is force also. So if there is tangential acceleration, the tangential force is mass into tangential acceleration. If there is centripetal acceleration, there will be centripetal force, which is mass into centripetal acceleration. And if there is total acceleration, the total force will be mass into total acceleration, where the total force is the vector sum of centripetal force plus the tangential force. So if you are wondering where these forces are, one force will be centripetal here, another force will be tangential here, the vector sum will be over here. The vector sum will be over here, just like the vector sum of the acceleration will be in this direction. Just like the vector sum of the acceleration will be in this particular direction. Thank you, Maiti. Thank you. Okay. Okay. Very good. All right. All right. Concentrate on the class. Concentrate on the class. Everyone. Yes. Then the next important thing which you should know in circular motion, there are some important terminologies. One second. One thing you have is the conical pendulum. Conical pendulum formula, very, very important. Please remember it. You have a pendulum like this and it goes in a circular path like that. It is hinged over here. The tension formula is there. The tension in the string formula is there, which is m omega square L. M omega square L. Many questions come. The tension in the string can be this much. What is the maximum speed by which it can rotate so that the string does not break? Standard question. Then you have a question where there is a road and it is just flat, it is just horizontal, and there is a vehicle which is going with some speed. What is the maximum speed of the vehicle on that horizontal road? Horizontal road. This is also a standard question. The maximum speed is given by root of mu s r g. Mu s r g. Keep this in mind. Very, very important formula. Mu is static friction coefficient, r is the radius of the road, g is acceleration due to gravity, everything in the root. But if the road is banked, if the road is banked like this, and then the vehicle has to go with some speed, then what is the maximum speed with which it can go? The formula looks very much like this. Instead, there is a small change. You will put mu s plus tan theta, where theta is this theta, which is also called as the angle of banking. This is a banked road, so angle of banking, upon 1 minus mu s tan theta, whole thing into rg, whole thing into rg. That's the formula for the maximum speed. There is another speed which is also called as the optimum speed. Optimum speed for very less wear and tear, such that the friction acting is 0, there is no friction, then that formula becomes root rg tan of theta. Root rg tan of theta. Very, very important. Okay, keep this in mind. Now, once this is done, I think most of the circular motion concepts are covered. There is one more small concept of circular motion which is coupled with work power energy. Let me just show that also to you. That's with regards to vertical circle. Where you have to give it enough speed so that it is able to just reach on the top. And for a string pendulum, or a block on a curved track, the formulas are very, very similar. The formula is the minimum speed required over here is root 5 rg, so that by the time it reaches here, the speed at the top becomes root rg. Only then the tension or the normal will be more than 0. But if it is not a string or a block pendulum, then if it is a rod pendulum, it's a light rod kind of a pendulum. A rod is suspended, then the rod will never compress. Only a string can compress, it can become slack. Only that's the reason why the minimum speed requirement is there here. If it's a rod, then the speed requirement is quite less. It is just root of 4 times rg. And at the top, the speed can be just almost 0 for a light rod kind of a pendulum. Is that right? Yes. Very good. Awesomeness. Thank you so much. On my way to ISRO, I'm pretty sure you will prove your name to be correct. Then let's go to SHM. Let me just create a duplicate. Simple harmonic motion. Imagine there is a wall and there is a spring over here like this.
and there is a block over here. Now what happens? You expand the spring and you release it so that it goes back and forth. So after some time, maybe, you know, the spring gets expanded and the block is doing some kind of a motion. Block is doing some kind of a motion. This is a snapshot at some time. This block right now over here, that was its natural length. But the yellow one which I am showing at some time instant when it is moving back and forth. So now imagine over here, okay, if this block has some velocity, there is some force also acting on it. There is some force of spring which is acting on it, right? The force of the spring is going to be this way. The force of the spring is going to be this way. And if I assume the acceleration to be like this, I know it is wrong. The value of acceleration that I will get will be negative. Also, I assume that the distance from the equilibrium, this particular distance is x. I have taken all these side variables as positive. So x, v, a, everything in that side. Then I will see that this force will be dependent on this x. This velocity will be dependent on this x. This acceleration will be dependent on this x. Because as this goes over here and here, you will see the speed, acceleration, force, x, every value is going to change. And this block is just going to oscillate back and forth, which will become a SHM, correct? Which will become a simple harmonic motion. Now what I do is I will imagine a circular motion which corresponds to this simple harmonic motion. Meaning, what I am trying to say over here, just try to imagine a circular motion over here, which is going like this, with some angular speed omega, such that if you drop a perpendicular, always the perpendicular falls on the block. So when this arrow mark is here, the perpendicular falls here. As the arrow mark shifts, it falls here. As the arrow mark shifts, it falls here. As the arrow mark goes here, the perpendicular comes here. As the arrow mark comes here, it comes here. As the arrow mark comes here, the perpendicular comes here. As it comes here, it comes here. As this rotates here, the perpendicular falls here. As it goes here, it comes here. And again back here. So as this performs circular motion, this block performs simple harmonic motion. This arrow mark has exactly this length. By the way, you know what is this? This is extreme position. Even this is another extreme position. And this one over here is always called as the mean position. So this length is the amplitude, which is often given the symbol A, which is also the radius of the circle. This circular motion which is happening, I call it as the phasor. So this is also called as the phasor of the particular, I'll call it the phasor of the particular simple harmonic motion. Remember that phasor actually is doing uniform circular motion. Can you see that, my dear warriors? Very good. In fact, if you notice one more thing, this angle, I can call it like this. Maybe initially, let's say over here, this phasor was here. So maybe the initial angle was phi. Maybe the phasor was here initially when time was 0. It could be anywhere. After some time it reaches here. That means this angle will be omega t. So this total angle is phi plus omega t. So if this angle is phi plus omega t, even this angle will be exactly phi plus omega t. This will be phi plus omega t. Now in this right angle triangle, this is hypotenuse. This angle's opposite side is this x. So can you not see, basically x is nothing but your A sine, you have omega t plus phi, sine omega t plus phi. Everybody is able to see that. So this is SHM, and you can see this is your circular motion, uniform circular motion. This is called as the phasor diagram. Yes, it's like your class 12th AC, correct. This omega, by the way, happens to be root of k by m. Also, all the formulas what you learned in circular motion are also valid. Like this omega is 2 pi by time period, which is also 2 pi into f. That's the reason why you can also write time period, which is 2 pi by omega. 2 pi by omega is 2 pi root of mass by spring constant. You can write all these things. It's perfectly valid. It's perfectly valid. From position, you can find every other, thing like velocity and all these things. So the formula for velocity comes out to be, differentiate that, it will be a omega cos omega t plus phi, and acceleration will be minus a omega square, differentiate this, sine omega t plus phi. This is in terms of time. You also get one more equation in terms of x, that is something like this, v is omega root a square minus x square. That's one more formula. And acceleration also you can write it in terms of x like this, minus omega square x. All these are formulas related to simple harmonic motion. One more thing which you should know is about the total energy of this SHM. The total energy of this SHM, which is kinetic energy plus potential energy, is going to be a constant, and that total energy is half spring constant into a square. Half spring constant into the amplitude square. Keep this in mind. Okay. A special case scenario of simple pendulum which you must be aware of. If it is a simple pendulum, that means the mass is here, this rod or string is massless of length L, then the time period is just 2 pi root L by G effective. Reason why I'm putting effective is because there are some lift problems where the pendulum is going up, down or accelerating, then you need to include pseudo force. Okay, so that's why G effective I have put. Another thing is for a physical pendulum or a compound pendulum where you hinge it over here, the center of mass can be somewhere else. The distance is over here. This is your pivot point. So that mass goes back and forth like this. This is called as a compound pendulum or just a physical pendulum. Then the time period of that is 2 pi. Here you have I, moment of inertia, I, divided by mass of the body into gravity into distance from the pivot to the center of mass. So mgd. That's the formula for a physical pendulum. Like you take a solid sphere, you put it at the top and or leave a rod and hinge it at the top and let it oscillate. Those kind of questions you will use this formula. Is that okay, everyone? Very good. Awesomeness. Moving on. Now, anything else is there in SHM that we have left out? I don't think so. Take a damped oscillations and all those things are not there. Superposition of SHMs, I will do it in waves, not over here. Okay, because it makes more sense to do it over there. Okay, otherwise I don't think we have left out any major thing. Small things, it's okay. Okay, right. Let's go to AC now. Let's go to AC because after that we'll be coming to waves. Okay, after that we'll be coming to waves. So in alternating current, one of the major formulas which you must be knowing for alternating current, if you have voltage which is positive negative, means changing the direction, that is called as alternating current, then that voltage might be a function like this. Maximum voltage may be sine omega t. Okay, it's a sine function. This is for, let's say, voltage. Maybe at the same time, let's say your current, let's say your current is like this. Okay, not that great diagram, but I'll try to draw it. This is current. You can see there is some phase difference between them. You can clearly see that the current is not together with the voltage. So there is some kind of phase difference. So maybe that current is I naught. You can have sine omega t plus or minus phi, anything, doesn't matter. This is your phase difference between voltage and current, and in alternating current, that's what you will see. The funny part, voltage and current do not go up and down together. There is some phase difference between them. There is some phase difference between them. What is V naught? V naught is this value. This is V naught. What is I naught? I naught is this maximum current that you get. This is I naught. You also have something called as RMS values. So V RMS, root means square, will be V naught by root 2. Also similarly, I RMS is I naught by root 2. If you ask me what is the average value of voltage, the answer is 0, of course. Whatever positive is there, that much negative is there. If you ask me what is the average current, I will say it is also 0. If you ask me how did you generate this, I would say, you just take a coil, and you just have to rotate it with some angular speed. Let's say the coil has an area A and n number of turns, and just make sure that the coil is rotating in a magnetic field. The coil is rotating inside a magnetic field. If you take the ends of the wire, you will see that there will be a voltage generated across it. That voltage will be magnetic field into area into omega into number of turns into this sine omega t. So if you notice, BA omega n is actually V naught. BA omega n is actually V naught. That's the maximum voltage which is reached, in any cycle. Keep this in mind. Now that you understand these basic terms, you will get questions on LCR. Okay, that is the main part of this chapter. I will be discussing that. Other things, transformer and all that, it is very simple. You can watch my lecture. That is fine. Main thing is this LCR. Let me just quickly revise that. So, if there is an inductor, resistor and a capacitor which is connected to a AC source, maybe the AC voltage is V, maybe the voltage across the inductor is VL, voltage across the resistor is VR, voltage across the capacitor is VC. But what will be same in all of them will be the current. The current flowing through all of them will be the same. Current is going to be the same for all of them. You'll be wondering whether voltage is not same. So will they add? The answer is no. A lot of people think the total voltage is VL plus VR plus VC. This is not true. What is true, in fact, is this. V vector is equal to VL vector plus VR vector plus VC vector. This is going to be true. You'll be like, okay, it's a vector, means what? You treat them like phasors. Because I know the AC voltages and currents vary like a sine function, simple harmonic motion kind of a wave, sinusoidal wave. And we saw this in SHM, that any sinusoidal function, any sine function can be treated like a phasor, a circular motion whose shadow, whose projection, whose component is the simple harmonic motion, right? That's what we saw. Then that rotating thing, that phasor, I can treat it like a vector, and it so happens that love, L for love is above everything. The inductor's phasor voltage is above everything, so VL is always on the top. Then comes resistor. Resistor could be anywhere. I'll just put it over here, but it is always perpendicular like this. And capacitor is always below. So VC is over here. Now these three phasors, if you compare it with the current phasor will be like this. This is the current phasor, my dear students. So the voltage across the resistor is always in phase. Voltage across the resistor is always in phase with the current. The voltage on the inductor is 90 degrees ahead, because omega is like this, is 90 degrees ahead of the current. The voltage across the capacitor is 90 degrees behind the current. That's the thing which you should remember. Love is above all, so VL. That's all. Now you will be wondering, so what next? So VL and VC are opposite to each other. So you can clearly see there will be a nice triangle which I can make, because this will be VL minus VC. If I subtract, sorry, actually I add these vectors. So this vector and this vector resultant will be only this much. Now I add it with VR vector. What I get is the total voltage. So obviously the total voltage magnitude wise, you can see it right from here using Pythagoras theorem, will be root of VR square plus VL minus VC whole square. So this is the correct way of writing it. This is not. You cannot just add the voltages 20, 30, 40. I cannot add it. I have to treat them like vector quantities. That's the idea behind it. Also, this voltage across each one of them, I can write it as current. Each of these voltages as current into the corresponding resistance. Like over here, I can just write it as current into resistance. Here, current into resistance of the inductor, which is called as reactance, and resistance of the capacitor, which is called as capacitive reactance. This capacitive reactance is 1 by omega C, and inductive reactance is omega L. If you are wondering, sir, I get confused whether it is 1 by omega L or omega L, 1 by omega C or omega C. Simple. What did I tell you about L? Love is above all. So inductors voltage always comes on the top, right? Always on the top. So it is always going to be in the numerator for omega L. It is not 1 by omega L, because 1 by omega L means it is down. Omega L is in the numerator on the top. So that's how I remember it. So naturally capacitor is below, so it goes in the denominator. A very simple trick. Not just that, you will also see that if you draw resistance like this, you can also draw XL over here, you can show XC over here. Combining this a little bit, you will see that this will be XL minus XC, this will be R, and their resultant, my dear warriors, is called Z, which is your impedance, which is nothing but your impedance. And this happens to be root of this square plus this square, because they are perpendicular. So R square plus XL minus XC whole square. Is that clear, my dear students? Durai, there is a lot of time for you to see it, because if you don't know the theory behind, then this revision session will not be of any particular use for you. Okay, so I suggest you watch it later on if you have not completed the syllabus. Another important thing in alternating current is for resonance. This is a special condition which happens. In that, you will see that the voltage across the inductor exactly equals the voltage across the capacitor. So they will cancel out each other. So the total voltage will be equal to the voltage across the resistor, because these two vectors will just simply cancel out. They will just simply cancel out. So the total voltage is in phase with the current. Here previously what happened, did you see the total voltage was not in the phase of the current. In fact, there was some phase difference. In fact, you can see there was some phase difference. Whether you measure it here or you measure it here, it's one and the same thing. But here what happened, the V, VR and I all are together. So you will see that the phase difference is 0. I can just say voltage and current are in phase. The total voltage and the current are in phase. And this also means because VL is equal to VC, it also means XL is equal to XC. Solving, what you get is that omega value, and this omega comes out as 1 over root LC. 1 over root LC. Keep this in mind. Not just that, let's also talk about the power loss. The power which is lost in a LCR circuit. That power which is lost in a LCR circuit is only across the resistor, because capacitor and inductor can never lose energy. They are conservative elements. They can store energy and give it back faithfully, but resistor is not like that. If it takes in, it will lose it permanently. So it is I square into resistance, which you can also write it as Vrms into Irms into cos phi. Okay, so you can write it as Irms into cos phi. This cos phi is also called as the power factor. Power factor. Vrms, Irms, cos phi, or I squared R, where I is Irms. Either way you will get the power loss. So in case of a resonating circuit, if you calculate the power loss, because phi is 0, can't you see that the power factor will be just 1? So power loss will be nothing but Vrms into Irms. That means this will be maximum. This will be maximum. Keep this in mind. Maximum is a maximum power loss that you can get. You cannot get more than this power which is delivered from the source to the LCR circuit. Okay, keep these things in mind. Right. Let's just do this and then we'll have a break. Okay, let's just do this because this is a small thing. After that, we'll come back to waves. I know everybody is hungry. Even I am hungry, but I'm just, wanting to complete this part and then we'll start. Longitudinal, shear and bulk. So we have done with AC, by the way, my dear students. Congratulations if you have made it till here. Let's go to these three different deformations. Longitudinal deformation is when you extend it like this. You pull it by applying some force and the length increases. Shear is where you slide the surfaces like that. So there is a force which is parallel to the surface. And bulk is usually for liquids where you change the pressure, of the liquid, because of which it either expands or it contracts. So talking about stress over here, longitudinal stress is that force which is perpendicular to the area. You can see this is the area of cross section. It is perpendicular to it. That's why it is that force which is perpendicular to that area upon area. Here the shear stress is the force which is parallel to that area. So that's why F parallel divided by area. The bulk stress is just how much did you change the pressure by. Just how much did you change the pressure by. The longitudinal strain is just given by the change in length. So it is x by the original length. The shear strain is given by your change in length upon the separation, which is h, which comes out that this is basically your x, this is basically your h. Here this was your x, this was your L. So which comes out as tan theta, where theta is this angle over here. Here the bulk strain or volumetric strain is the change in volume upon original volume. When you divide both of them, what you get is the modulus. So Young's modulus is this stress by this strain, longitudinal by longitudinal strain. Here you get modulus of shear, which is G. So it is shear stress by shear strain. And lastly, here you will get bulk modulus, which is bulk stress divided by bulk strain. That's all, divided by bulk strain. This is how you calculate each of these things. That is the main agenda in this chapter. And one small thing which is there is where you need to know about this particular stress versus strain graph, how it changes. First, it is straight line. When it is a straight line, the stress is proportional to strain. Then it is supposed to obey Hooke's law, where it is proportional. Then suddenly it becomes non-proportional. All right. But at least it is two-way, meaning if you load it here and unload it, it will follow the same path and it will come back here. Just like if you load it and unload it, it will come back to the origin. So it is elastic in nature. It is basically elastic in nature. After this, it goes into something called as the plastic zone. This is your plastic zone. This point till where it remains elastic is called as the yield stress. This is completely your elastic zone, my dear warriors. Elastic. It was elastic in nature. That means it retains or regains its shape. But once it is in the plastic zone, if you elongate it and release it, it will come back to some other point. If you notice this point, there is no stress but there is strain, meaning that it has been permanently deformed. This is also called as permanent set. And this can continue only till one point over here. After that, it just fractures. You cannot load it infinitely. This is your strength. This is your strength of the material. This is the strength of the material. This is the maximum loading that you can do on it. After that, it will just break or it will fracture. Not just that, if you happen to measure the area under this graph, then that area will give you how much energy is stored per unit volume, which is also called as energy density, and that also happens to be half stress multiplied by strain. Half stress multiplied by strain. So keep these things in mind. Okay, yeah, now I'm able to see. Let's begin with the next part of this session, which is nothing but your waves, where I'm going to do all the three waves together. Okay, starting off with the comparison of the three waves that you have in your JEE main syllabus: transverse, sound and electromagnetic waves. So if you talk about transverse wave, that means a wave on a string. You take a string and you generate a pulse and it goes like this. So it is a wave on a string, basically. That's a transverse wave. The equation is something like this: A sine, you can have kx plus minus omega t, anything, or you can also have omega t plus minus kx, Whereas for sound, what happens is you have compression and then rarefaction. Then again you have compression, then again you have rarefaction. Instead of crest and trough, you have compressions and rarefactions. So you get a pressure wave equation. P is equal to maximum pressure variation Pm into sine or cos, does not matter. Omega t plus kx, omega t minus kx, does not matter, depends on the direction. That is what you get. But along with the pressure, the molecules also go back and forth. So there is a displacement which is occurring. That displacement is given by Sm Instead of sine, this will be cos, because pressure and displacement are always 90 degrees in phase difference. That is some point which might be rarely asked, but I felt you should know this. If this is sine, this is cos. If this is cos, this is sine. So this will be again omega t plus minus your kx. This is the displacement. This is the pressure variation. This is a displacement. Each particle displaces back and forth like a SHM, and the pressure also changes, but the pressure and displacement are 90 degrees in phase apart. Keep that in mind. Everybody is present. Very good. Next, electromagnetic waves. In this case, you have two things. One is the electric field which travels, and the next one is the magnetic field which travels. Magnetic field which travels like this. Both of them are perpendicular to each other. One is magnetic field, one is electric field. That's why the name electromagnetic. If the electric field equation is E naught sine omega t plus minus kx, then the magnetic field equation is B naught same sine omega t plus minus kx. That's how it looks like. Okay, these are the wave equations for all of them. Oh, by the way, these two terms are related to each other. Let me tell that as well. PM, pressure amplitude, is bulk modulus into K into SM. I know you might be wondering what the hell is this K. I will come back to it over here. So when we describe a wave, then from one crest to the next crest, that is called as the wavelength. This height is called as the amplitude. And we know that the wave speed, that is the speed with which the wave goes, is given by frequency into wavelength, where this frequency is just 1 by time period. This frequency is just 1 by time period. Then you have these terms called as angular wave number in general. Angular wave number. This is 2 pi divided by wavelength. It is always expressed in radians per meter. Radians per meter. That is what it is expressed in. Keep that in mind. Angular wave number. You also have angular frequency. Angular frequency exactly like this, which is omega, which is 2 pi. Instead of lambda, you have time period, which you can also write it as 2 pi into f. So the K you see over here, K is the angular wave number, B is the bulk modulus, which I told you before, SM is the maximum displacement, PM is the maximum variation in the pressure. Okay, I don't think the session will go on for a very long time, maybe 1.5 hours more. Is this E naught and B naught related to each other? Yes. In fact, you can see that the wave speed, which is the speed of light, is like this. This C can be written down as E by B or even E naught by B naught. E by B or E naught by B naught, one and the same thing. You can also write it as omega by K. Omega by K, that is standard. In fact, that is true for all of them. There is nothing great. So in fact, I should not even put it over here. So in fact, I should put it on the previous slide. So this V is also omega by K. This is also this omega by K, standard thing. Okay, it's true for any wave, doesn't matter. But there are some special formulas for finding this wave speed. Apart from E by B, E naught by B naught, here you can also write it as 1 by root of permeability into permittivity. This permeability and permittivity are electromagnetic properties of the medium. So if the medium changes, the permeability and permittivity will change. We have discussed this some time back in the same session. So the speed of light will also change. Keep that in mind. In case of transverse wave, the wave speed is given by root of tension by mass per unit length. This mu is always mass per unit length. Keep this in mind. In case of sound, it depends whether it is solid, liquid or gas. If you are talking about solids, then it is root of, instead of tension, here you have Young's modulus, and instead of mass per unit length, you have mass per unit volume, which is simply density. If it is a liquid, then it is root of bulk modulus by density. If it is an ideal gas, then the bulk modulus happens to be gamma times pressure, so divided by density, which is, you can also write it as gamma RT by M, gamma R temperature by molecular weight. That also will do. Okay, these are the formulas for wave speed, for wave on a string, for sound waves and electromagnetic waves. One special thing about electromagnetic wave is this c, which you see over here, the speed of light, is parallel to the cross product of electric field with magnetic field. If you do E cross B at any place, you will basically get the direction of C. So in this case, if I do E cross B, I am seeing it is coming this way. So the direction shown over here should have been changed. So it should ideally be coming this particular way. Because you can see first the bulge, the crest of the electric field is on the top. The first bulge of the magnetic field is towards the left side. So if you do electric field cross magnetic field, it is coming out to be in this particular direction. Now, a transverse wave also delivers power. It also has energy in it. So we have to also talk about the energy given by a wave. So the power of a wave, the average power of a wave is half mu v a square omega square. Mu is mass per unit length, v is the wave speed, a is the amplitude, omega is angular frequency. That is again a standard. Okay, keep all these things in mind. Dear students. Yes, the power formulas, and you can see every time power, energy, etc., they are always, they are proportional to the square of the amplitude. They are always proportional to what? The square of the amplitude. Keep that also in mind. Right? You can see that they are always proportional to the square of the amplitude. Here, instead of power, here you have intensity, and that is half pressure amplitude square by density. Pm square by rho. It is again proportional to the square of the amplitude. Pm amplitude square of it. Here, in this case, the intensity of the light is given by half maximum electric field. So that means I will have E naught into, you have that maximum magnetic field, that is B naught, the whole thing divided by mu naught. That is the formula that you have. E naught B naught by mu naught. Is that okay, my dear warriors? Keep all these things in mind. Again, you can write E naught in terms of B naught with C, or B naught in terms of E naught with the C. You can do all those variations. So that is the intensity of the electromagnetic light. Okay. Having said this, will I need another slide? I'm not sure, but I'll just keep this handy. Few more things with regards to all these waves. In electromagnetic wave, you have one thing with regards to reflection or rebound. If light goes and hits a surface and rebounds, then on the surface which it hits, it exerts a force. What does it exert? A force. That force per unit area is called as radiation pressure. Radiation pressure. That radiation pressure is equal to I by C or 2I by C, depending on whether that surface is absorbing or whether it is reflecting. or whether it is reflecting. Keep these things in mind. Cool till this point? Radiation pressure by light, electromagnetic wave. Intensity by speed of light. If it is completely absorbing, if it is reflecting, then it is 2 times of that. Here we don't have any radiation pressure and all of that. With regards to reflection and all of that, you need to know one thing. If a wave is going in as a crest and there is a fixed end versus there is a wave which is going towards something called as a free end. This is a fixed end, this is a free end. And the same thing over here, you have a compression which is going towards a fixed wall. Compression which is going towards a fixed wall versus you have a compression which is going like this, maybe from a dense medium, dense to rare medium. Here you can see this is rare and this is dense. You will see the reflected sound or the wave is completely different in both these cases. In case of transverse wave, the reflected wave will become a trough if it is a fixed end. If it is a fixed end, then you will see the phase inversion happens. Phase inversion happens. But for a free end, you will see that the reflected wave is in phase. There is no change in the phase. There is no change in the phase as compared to the incident wave if the end is free. Whereas in longitudinal waves, it so happens exactly opposite. A compression which is incident on a denser medium will come back as a compression. Rarefaction will come back as a rarefaction. And in case of dense to rare, the reflected sound will come back as a rarefaction. So here there is no change in phase. Whereas here I would say there is phase inversion. This phase also brings me to one more point regarding a wave. If you choose any 2 random points, could be anywhere, let's say one is here, one is here, they are probably separated by some distance delta x. Maybe one particle is going like this, one particle is going like this. So there is some phase difference between them. There is phase difference between these 2 particles. The phase difference between those 2 particles, delta phi, is given by 2 pi by the wavelength into the separation of the 2 particles. This is used in many situations where you have to find the phase difference of the 2 waves arriving at a point, or two points are there on a wave. What is the phase difference between those 2 points? Those kind of questions can be solved using that. Yes, radiation pressure can be done in modern physics also, can be done over here also. It's there in both the chapters. If I do it here, I will not do it in modern physics. Understand that? Okay, cool. Now let's come to the interference part once we have learned this. Okay, so what happens is, if you have a wave of amplitude A1 going like this, and you have another wave of another amplitude, let's say A2, coming like this, you can see that between these 2 waves there is some small gap. They are not coming in together. That means there is a path difference. There is a path difference. I will call it as delta x. Because of that path difference, there is a phase difference. So therefore there is a phase difference given by delta phi, which we have already seen, 2 pi by lambda into delta x. So this particle here and this particle here, there is some phase difference between these 2. These 2 come together and then they interfere with each other. So there is a phase difference. When these 2 waves combine together, when these 2 waves are combined together and joined, then they are said to interfere, and I am superimposing them.
superimposing them. That means every wave's characteristics I'm retaining, but I'm also adding other waves characteristics over it. So it's like, you know, when there are many kids in a classroom, one kid is talking, another kid is talking, another kid is talking, everybody's sound will come. So they are getting superimposed, and once they get superimposed, they will interfere. And what they end up doing is they produce a wave which is called as the resultant wave. A resultant wave of a new amplitude, of a newer amplitude. Is that clear? That is a new wave of a resultant amplitude A. Now, to find this amplitude, what you must do is use the phasor concept. Each oscillating quantity can be thought of as a circular motion's projection, shadow or component. So think of this wave as a phasor being created by this arrow mark over here. Let's say I call it as A1. Maybe this A2 has another phasor. I will call it A2 like that. This is A1 over here. This is A2 over here. The reason why I have shown it at different angles is because there is a phase difference between them. So there is a phase difference of delta phi. So I'm superposing two SHMs, two waves, two things which are oscillating, two alternating circuits, whether voltage, current, doesn't matter. Everywhere the concept is same. There will be a resultant produced. And how do I know the resultant? By vector addition. By vector addition. Treat them like vectors. We have used the parallelogram law here. You can also use triangular law. So this will be A. So remember, this A bar is equal to A1 bar plus A2 bar. This is basically vector addition of the phasors of the waves. Hence, I can also say the resultant amplitude is A1 square plus A2 square plus 2A1 A2 cos del phi. That is the answer for the resultant amplitude. Is that clear? Not just that, I also know one more thing, and that is intensity is proportional to amplitude square. And I saw that every single time. Power is proportional to amplitude square. Intensity is proportional to pressure amplitude square. Here also, if you rearrange, you will see it will be E naught square or B naught square. So basically it is always proportional to the square of the amplitude. So hence, oops, my God. Okay, the board has become slow because there are many pages on this. Okay, so this resultant wave's intensity, the resultant wave's intensity will be root of, no, there will be no root in this case. It will be just intensity of wave 1 plus intensity of wave 2 plus 2 times root of I1, I2, and outside the root you will have cos of delta phi. That is for the resultant intensity of the wave if I know the individual intensities. Is this part clear, my dear students? Okay. Superimpose means adding the effects. I just explained that. Okay. Now, having said this, 1 second. Yeah, over here you will have two kinds of interferences which you must be aware of. One is this one, where both are in phase. This is A1, this is A2, and you add both of them, and the resultant amplitude that you get is very large. This kind of interference is basically called as your constructive interference. In such a case, amplitude is just
simply put A1 plus A2. Here you will see that the phase difference between them is either 0 or 2 pi or in general 4 pi or basically any, in general I can say even number of pi. Even number of pi. In fact, the path difference can also be 0, lambda, 2 lambda, like that. In general, any n times of lambda. The intensity that you get comes out as root I1 plus root I2 whole square. That's for constructive interference, where crest meets crest, trough meets trough. Then the next one, where one of the waves trough meets the other wave's crest. So one is A1, one is A2. When you add both of them, what you get is a wave of smaller amplitude A, and this A will be the modulus of A1 minus A2. This is obviously going to be called as destructive interference. Destructive interference. In such a case, the phase difference between them, they will be opposite to each other. So pi, 3 pi, in general basically odd times of pi, that will work. And the path difference will be lambda by 2, 3 lambda by 2, in general odd times lambda by 2. That's what you will get. In general, odd lambda by 2. Okay, keep this in mind. Next important thing which you should know is the intensity of the resultant, which will be now the least intensity. Here this will be maximum intensity. If you open up previous year papers, you will see many questions are based out of this. Many questions. Max by min is this, find I1 and I2 and all of that. So this will be root I1 minus root I2 whole square. Right? This is the minimum intensity formula. This is useful for all kinds of things. Now there are many phenomena based out of interference. One such phenomena which you must be knowing is beats. Is basically beats. This is there in the syllabus. Doppler effect has been removed. So where you have one wave of one frequency, let's say F1, okay, and another wave of almost similar frequency F2, and when you superimpose both of them, what you get is a wave looking like this. So you get loud sound, and then faint sound, and then you get loud sound, and again you get faint sound. So the duration from one loud to the next loud, I call it as the beat period, or from one faint to the next faint, I call it as the beat period. Then you have something called as the beat frequency. The loudness and the faintness, it keeps on alternating. So you have the beat frequency, which is given by modulus of F1 minus F2. This beat frequency is nothing but 1 by the beat period. 1 by the beat period. That's all. It's F1 minus F2. Whichever is bigger, you put it first, or you just subtract them and make it positive by making it modulus. Is that clear? Everyone? Mahesh, don't spam, bacha. Don't spam. Right. Then another concept of interference used in light is in YDSC setup. Standard formulas, I will just give it to you so that you know all these things. This is the central part of the screen. Here you will have two slits. They are separated by some distance d. This is S1, this is S2. This is your screen, right? And here you have your basic light source. The light will go here, the light will go here, and then that light will go and interfere at some point on the screen over here. And standard things given in these kind of things are this distance, then this is y, and this angle is given as theta, all of that. So what and all things you must know. For basically this is a Young's double slit experiment. YDSE, Young's double slit experiment. Standard formulas which you must know. First thing, if D, distance from the source and the slits and the screen is large as compared to the slit distance, then the path difference of the two waves, which is nothing but S1p minus S2p, is approximately D sine theta. This is very important. Then the next approximation comes, if theta is small, then sine theta is approximately tan theta. That will be nothing but your y by d. And this is also going to be theta. And this you can use if your d is much larger than lambda, then you are most likely interested in the smaller order interference. Theta is small is only true if d is much larger than lambda. Then you use this approximation. Then you have two formulas for bright fringe and dark fringe. For bright fringe or maxima, what is the formula that you get? The y coordinate of any point on the screen is given by n times of lambda capital D by small d. Whereas for a dark fringe, the formula is odd times the lambda capital D by small d by 2. And then you also have the fringe width formula, beta, which is just lambda capital D by small d. Very important. In this, remember, when you dip this medium in a different solution, lambda will change, accordingly beta will also change. Okay, these are basic things which you must be very aware of. Okay, so that's with regards to the interference part. And the last thing in interference is about the standing wave. Standing wave is basically formed when you have two waves going in the opposite directions. One wave is coming like this, another wave is coming like this. When they superimpose, then what you get is a standing wave. The standing wave looks something like this. In such a case, what happens? The energy does not go anywhere. Each of them is called as a lobe or a loop. This point over here, which does not move up and down, they are called antinodes. Whereas this region, what did I say? Sorry guys, these are called as nodes, my bad. These are called as nodes. And the region with maximum displacement, these regions, they are called antinodes. You will also notice a lobe, which is from one node to another node distance, is exactly half a wavelength, because you can see this is one wave. So this is half a wave. So it is lambda by 2. Keep this in mind. This is lambda by 2. Nodes never go up and down. Antinodes move up and down by a lot of amount. Okay. The equation of such a wave is given by this. Y is equal to, if each of these waves had an amplitude of A and A each, then this is given by 2 times of A. You can use sine also, or you can use cos also, doesn't matter. Then you will have kx into, there is no plus minus, remember. Here also you can use sine or cos, does not matter, again into omega t. Keep this in mind. Okay, so it is a product of sine kx and cos omega t. It's not kx plus minus omega t. This is the equation of a standing wave. Is that clear, my dear warriors? Keep all these things in mind. Okay, next, the transverse wave, standing wave and longitudinal standing wave. Okay, so what are the key differences? Let's have a look. Let's have a look. So what you do, you create a wave and let it get reflected from an end. So now you will have two waves, one which is falling onto it and one which is getting reflected. So now you have two waves going in opposite direction. So that will create a standing wave, either on a string or on a pipe, in a pipe. So you speak inside a pipe, so the sound will go back and come. So you have two waves going in opposite direction, it will create a standing wave. So my dear warriors, in such cases, please remember few certain things. Always, wherever you have fixed end, always, wherever you have a fixed end, you will have a node. Fixed end is always a node. Here, if you have a closed end of the pipe, closed end of the pipe, closed end of the pipe, here also you will have a node, you will have a node of the displacement. You will have a node of the displacement, that means the particles can't go anywhere. So this is your standing wave, like you can see. You can see there is a node which is formed over there. There is a node which is formed over here or here. If you have a free end, if you have a free end, then you will see an antinode. If you have a free end, if this end is like free to move up and down, if this is a free end, then 100% what you get over here is nothing but an antinode, maximum displacement. For a pipe, this must be an open end. This must be an open end. That means it is open to the atmosphere, and the antinode that you get, something like this. Okay, I hope you can see that antinode, everybody. That's an antinode right over there. Right? That is an antinode right over there. So you will have a displacement antinode. Displacement antinode. Keep this in mind. But there is a catch, especially in longitudinal, that means sound, when organ pipes. So these are organ pipes, pipe is reflecting that sound back and forth. Or there is a small problem. The problem is over here. You can see the antinode is not exactly on the open side, it is slightly outside. This is called as the end correction. The antinode is slightly outside, so the length should be slightly more, whatever you consider for the calculations. So the end correction is always 0.3 times the diameter, where this is your diameter. This is the diameter of the pipe. That is one correction which you need to inculcate in case the diameter is huge. If the diameter is small, then this value is small. You can neglect it in many cases. Not just that, one more thing which many people do not know is that whenever there is a displacement node over here, actually it will be a pressure what, guys? It will be a pressure antinode. It will be a pressure antinode. Why? Because displacement and pressure are always 90 degrees in phase. So when one is maximum, one is minimum. When this is minimum, that is maximum. So that's why if there is a node here, pressure wise, there will be maximum pressure variations. So closed end always experiences maximum variations of the pressure. Whereas an open end is open to the atmosphere. So it will equalize the pressure. It will maintain its equilibrium. Pressure variations are very less. So there will be pressure node. There will be pressure wise, it will be a node. In this case, there is no problem. Only problem happens over here. Keep this in mind. Cool. Shall we go ahead? Next one. Now, whether it is a transverse wave on a string or longitudinal wave on longitudinal wave in a pipe, the formulas for both of them are same when both sides are closed or both sides are fixed, or one side is closed, one side is open. That means one is fixed, one is free. Or both are open, that means both sides are free. It's the same thing. So let me just draw all the three diagrams. First case where you'll have this. Oops. Something like this. Or in the pipe, something like this. Okay, both sides are fixed, both sides are closed. This is one possibility. The second possibility is this is free, this is also free, so you get antinode here and antinode here, both sides. Same thing over here too. Oh, sorry, this is open. This is an open pipe. So you will get like this or like this, open on both sides or free on both sides. The last one is this, where one side is fixed, other side is free. One side is fixed, other side is free. So you'll have a node here and antinode on the other side. Here you will have one side closed, one side open, one side closed, one side open. So it will be something like this, right? So these are the only three possibilities. And what are the formulas for each one of them? Let me tell you. First of all, whether it is fixed on both sides or free on both sides, closed on both sides or open on both sides, the formulas are same. That's the best part. The formula is F is equal to N times V by 2L. It's the same for this and this. There is no difference at all. It's the same here, it's the same here. I'm not rewriting it on both sides. Okay, it's the same for both of them. For both of them, keep this in mind. Okay, same here. That means I can say the frequencies are F, 2F, 3F, etc. Okay, basically N times of F naught, I will call it F1, 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 F1. What is F1? F1 is the first frequency, which is V by 2L. F1 is the first frequency, which is basically V by 2L. All multiples are present. That means I can then say all harmonics are present. All the harmonics are present. All the harmonics are present. This F1, which is V by 2L, is also called as the fundamental frequency. That is also called as the fundamental frequency. Keep this in mind. Whereas in this case, when open, closed or free, fixed is there, the frequency is given by odd times V by 4L, not 2L, 4L. Because of which frequencies will look like this: F1, 3F1, okay, 5F1. In general, odd times of F1. Again, this fundamental is V by 4L. Please mind it, not 2L. This is your fundamental. This is your fundamental, and I can say only odd harmonics are present. Odd harmonics only are present. Only odd harmonics are present in this case. Right? Everybody with me? Very good. Excellent. All these are important things. Okay? You will 100% get questions on this. Whether it is an organ pipe or whether it is a standing wave on a string. So these are basically your string type instruments. String instruments. String instruments. This is your string instrument. This ones are basically your organ pipes. Organ pipes. String instruments are like sitar, guitar, all these veena, all these are string instruments. They follow these formulas. These are organ pipes, means trumpet, flute, right? You can change the length of the flute, you will see the sounds will change. There you use these formulas. Okay? Thank you for putting up that fire, J Achiever 1. I need it. I need a lot of fire. Right. So we have completed waves now. It's time to go on to what is it? Mirrors, reflection, refraction. So we are coming slowly towards the end of the session. After reflection, refraction, we have just thermal physics and modern physics. So it's going to finish very soon. Wow, nice. Okay, so I had expected that we will finish in 3 hours, but looks like nicely we have taken time, but that's okay. I think one session to complete physics, imagine, very few teachers do this, and that too without any printed material on the screen. Okay, so it's all there over here right now. All right, so let's
let's start with plane mirrors. What are the important formulas that you should know regarding reflection and all of that? Standard things, so everybody knows. This thing, if this is angle of incidence, this is angle of reflection. Angle of incidence is angle of reflection. This is reflected light from the mirror, and the deviation is 180 minus 2i, standard formula which you must know. Also, one more question can come where a mirror is rotated by theta. So what happens? The light which was reflecting like this now will go like this. So there is a, you can see there is a change in the angle. That change in the angle will always be 2 times of theta. So the light which was falling now, because the mirror got tilted, the reflected light will tilt. That reflected light will tilt by 2 theta. That's a standard result. Please remember it. Okay, that's another formula. Then also, what you should remember in a plane mirror is if you have 2 mirrors inclined at an angle, theta, then if a ray of light falls here and reflects, the total deviation is independent of the angle of incidence, and the total deviation is 360 minus 2 theta. 360 minus 2 theta. Very, very important formula, independent of the angle of incidence. Another important thing with regards to inclined mirrors is that if you have mirrors inclined at an angle and you place an object over here, you will see that there will be images which are formed of it in a circle. There are images which are formed, I1 to In, images which are formed in a circular path. Finite images are formed. The number of images formed will depend on whether 360 by theta is odd or even. 360 by theta is odd or even. So the number of images will be given by 360 by theta if this is odd, but if it is even, then you will make it 360 by theta minus 1. This is if it is even. If the value of 360 by theta is odd, it is as it is. If 360 by theta is even, then you subtract 1 from it, again make it odd. Always odd number of images are seen in a circular format. Okay? Clear till this point? Moving on to the next one. If you have a mirror which is itself moving with a velocity Vm, if you have an object moving with velocity Vo, then the image will move with velocity Vi, which is given by 2Vm minus Vo. 2Vm minus Vo. Very, very important formula, my dear warriors. Okay, which you will definitely need in many questions. Will definitely need in many questions where mirror, etc., everything is moving. So this is with regards to plane mirrors, most important formulas. Other things I think we should not discuss so much over here. Okay, then refraction. In refraction, what and all things are very important? Let's have a look. You have a medium. This is the normal. Okay, and from here the light comes and goes here like this. This is incident. This is refracted light. The medium on the top might have refractive index mu1. The medium below has a refractive index mu2. Okay, 1 and 2 are the labeling which I have done. Okay, then by Snell's law, I can just say sine of angle of incidence by sine of angle of refraction is mu2 by mu1, which is called as 1 mu2, which is also reciprocal of 2 mu1, Not just that, I can also say this is speed of light in medium 1 by speed of light in medium 2, which is useful in many problems to find the speed in a different medium. This is also called as refractive index of 2
with respect to 1. This is called refractive index of 1 with respect to 2, reciprocals of each other. And this can be also written down as f into lambda 1, f into lambda 2. In fact, that f will get cancelled out. That f will chumma get cancelled out, right? It is just going to get cancelled out. It will be just lambda 1 by lambda 2. Mu 1, mu 2 are basically absolute refractive index. This is a relative refractive index. These are basic things which you should know. Not just that, you should also know that the incident light was actually going here. It has deviated by some amount. It has deviated by some amount. That angle of deviation is I minus R, but sometimes R can be more than I. So you will put a modulus symbol. This is for refraction. Please understand. Many students do not know this, that they feel delta is always 180 minus 2i. No, no, no. 180 minus 2i is for mirror. For refraction, it is I minus R modulus. I minus R modulus. Okay? Everybody with me? Awesomeness. Now the next thing which you must know in refraction is that apparent depth, apparent height concept. So please understand this. If this is a dense medium and this is a rare medium, and it so happens that the observer is here, and the observer sees an object, and then he will see that the image is slightly above, that means closer. This is called as apparent height. This is called as the apparent height, and this one is the actual height, h naught. This one is the actual height, h naught. This apparent height will be actual height divided by mu. Divided by mu. Mu is the refractive index of the dense medium with respect to the rare medium. That's what is important. If you are in air, you see the bottom of the swimming pool, it appears closer. That is where the image is formed. Actual depth is this much, HO. HO is this complete depth. Understand that? But H prime is the apparent depth. Same way, if an observer is here, then an object placed here, the image will be formed slightly above. This will be the actual height of the object, but this whole distance will be the apparent height, and that apparent height will be actual into mu. Actual into mu. Is that clear, my dear students? Is that clear, my dear students? Everybody with me? Very good. Then the next concept which comes is regarding the glass slab, where you have a glass slab, and you have an observer over here. You have an observer here. Just 1 second, guys. Yeah, so the observer is here. He will see whatever is there behind, it will shift. That shift, because of a glass slab of refractive index mu and thickness T, is given by thickness into 1 minus 1 by mu. 1 minus 1 by mu. This is also very important, especially with regards to those problems where there are multiple layers of liquid and you have to see through them. Each layer can be treated like a slab and each layer will cause a shift. So whenever you have those multiple layer problems, mu1, mu2, mu3, etc., then I can say that the total shift will be the sum of all the shifts. These kind of questions are also there in those glass slab questions, right? Everyone? Very good. Excellent day. Electrodynamics done almost. Electrodynamics almost done. Yeah. I don't think we left much, right? Okay. Then. Next thing. Prism formulas. Let's have a look. if you have a prism of angle A, and then let's say the light enters here, this is the normal, it goes like this. This is angle of incidence, internal angle of refraction, sorry. Here if I draw the normal, another angle R2, and finally emerges out at an angle of emergence I2. This is called as the incident ray. This is called as the emergent ray. This is called as the emergent ray. What are the important things that you should know? What are the important things that you should know? First of all the geometrical formulas. What are all the geometrical formulas? The angle of the prism is R1 plus R2. That's the first formula which you should know. Okay, angle of the prism is the sum of the internal angles of refraction. Okay, next formula, Snell's law is applicable. Snell's law is applicable. That means mu is sine of I1 by sine of R1. Sine of I1 by sine of R1, or sine of I2 by sine of R2. Sine of I2 by sine of R2. That is another formula. Not just that, you will see the ray was actually supposed to go here, but finally it went here. So clearly there is a deviation which is produced. Clearly there is a deviation which is produced. That is I1 plus I2 minus A, minus the angle of prism. Keep this in mind. Minus the angle of the prism. Is that okay? These are all some important formulas with regards to the prism. Now the next formula which comes is with regards to least deviation. So when we actually, let me show it on this slide only. If I draw the graph of the deviation versus the angle of incidence, that graph looks in a very peculiar manner. It is symmetric and it looks like this. It is symmetric and it looks like this. So you choose different angles, R1, R2 will change, I2 will change, I1 will change, I2 will change, delta will change. The graph looks like this. It is a symmetric graph. You will see that there is one peculiar value for which delta is minimum. Delta is minimum. That happens when I1 is equal to I2. That happens when I1 is equal to I2. And when that happens, the ray inside is parallel to the base like this. This is incident. This is emergent. 1 second. This angle I1 and this angle I2. This is for minimum delta. I1 will be equal to I2. Not just that, even these two angles R1 and R2 will be also equal. R1 will be equal to R2. And you will see one more result which holds true, that is the refractive index. Refractive index is sine of angle of prism plus delta minimum by 2. This is not any ordinary delta, only minimum delta. You can't use any other delta, upon sine of A by 2. Keep this in mind. Okay, sine of A by 2. Okay, very, very important. And you can see the line here is parallel to the base. Very, very crucial. Now, there is a special case of this where you have basically not just any prism. In fact, you make the prism very, very small. A is small. So then the prism looks something like this. The prism looks something like this. Then that is called as a thin prism. So theta will be sine theta, which will be almost tan theta. These approximations are valid. And then what also happens is the graph of deviation versus angle of incidence, almost looks like this. So whether it is minimum deviation or any other deviation, they are all going to be almost the same value. The deviation is almost the same. So delta m approximately equals any other deviation, and that deviation comes out to be angle of prism into mu minus 1. Angle of prism into mu minus 1. Very, very important formula again. Okay? Keep these things in mind. Keep these things in mind. Cool? Shall we go ahead, my dear students? Shall we go ahead, my dear warriors? Do let me know in the chat box. Full of energy, full of josh. Okay? Next one. Mirrors and refraction, the formulas. So whether you have a concave convex mirror like this. So when you have concave mirror, this is your convex mirror. This is the center of curvature. This is the focal point. This is the center of curvature. This is the center of curvature. This is your focal point. Meaning the rays which were parallel, they will pass through the focus, and the ray which was going through the center of curvature, that will still pass through the center of curvature. Same way over here, if a ray was parallel, it will diverge from the focus, and by chance somebody hit on the center of curvature, then it will rebound at the same along the same line. You will see in such cases, in mirrors, that is curved mirrors, the radius of curvature is 2f. Radius of curvature is 2 times the focal length, or f is r by 2. That's a standard result. Whereas for lenses, whether it is convex lens like this or a concave lens like this, convex lens like this or a concave lens like this, each of them will have a center of curvature. Each curvature could be different. Like this curvature, if you see, it's a part of this circle, center might be here, it might have some radius. This circle, if you see, it has a center of curvature here. Same way here, this curvature might have center here. This curvature, if you see, might have some center over here, right? So looking at their center of curvatures and radius of curvature, you get the focal length, which is given as the lens maker formula, which is the refractive index of the lens with respect to the medium. So you can also write it as refractive index of lens upon refractive index of medium minus 1 into 1 by R1 minus 1 by R2. What is this R1 and R2? What is this R1 and R2? The radii of curvature, right? Like radius 1 will be this one, radius 2 will be this one, correct? Similarly, this will be R1, this will be R2. Can you see that? Those are the radius of curvature. Many people get confused, especially when the lenses are dipped in water. They write mu L minus mu M. No, 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 no. It is mu L by mu M minus 1. Relative is not A minus B. Relative is A by B for refractive index. Okay? Alright. Yes, Gokul will be doing it for NEET also later on when the NEET exam comes very close. Also keep in mind, you also have the power formula. You have the power formula. Power for a mirror is minus 1 by f, whereas power for a lens is 1 by f. That's the difference. Power is the degree of convergence or divergence. So if it is basically converging, if the rays are converging after reflection or refraction, it is positive power. And if the rays happen to diverge, it is said to be negative power. That's all. Okay, as simple as that. Then you have the lens formula and the mirror formula. Mirror formula is simple. 1 by v plus 1 by u is equal to 1 by f. If you know the object distance, if you know the focal length, you can find where the image is formed. Here, it is just 1 by v minus 1 by u is equal to 1 by f. Instead of plus, there is a minus sign. U is object distance, v is image distance. Then the next thing that you get is the magnification, which is height wise, which is height of image upon height of object. This is also called as lateral magnification. In case of mirrors, it is minus v by u, whereas in case of lenses, the magnification which happens height wise, height of image upon height of object is plus V by U. That's all. If there is minus here, there will be plus here. You can see signs are just opposite. Lastly, you also have the formula for magnification longitudinal wise, meaning along the principal axis, which is length of the object along the axis, length of the image along the axis upon length of the object along the axis. Same thing over here, magnification longitudinal is length of the image along the axis upon length of the object along the axis. Here it is just minus of V square by U square, or you can also put it as V by U whole square with a minus sign for mirrors. For lenses, it is just V by U whole square. So it is always going to be positive here, it is always going to be negative here. Not just that, this also happens to be equal to one more quantity, that is velocity of image, especially those problems where image and object are moving, upon velocity of the object. This also is equal. Very important. Longitudinal magnification is the ratio of the velocities. This is also velocity of the image upon velocity of the object. Keep this in mind. Very, very crucial. Shall we go ahead? Yes, all these are formulas for mirrors and lenses. Standard, another formula which you might be using later on will be combination of lenses. Okay, so when you have combination of lenses, just make sure 1 by effective power, 1 by effective focal length is 1 by f1 plus 1 by f2 plus 1 by fn. Basically the effective power is just p1 plus p2, like that. That's all. You just add the powers or the reciprocal of the focal lengths like resistors in parallel. So that formula is also very, very useful. Cool. So that is with regards to optics, my dear students. These are the most crucial formulas which you are going to need. Right? Very good. We can even talk about the optical instruments part just in briefly, optical instruments formula. Optical instruments formulas. The first thing is for a simple microscope, also called as the magnifying glass. The magnifying power, this is not to be confused with power. Power is 1 by f, dimensionally it is 1 by length. It is expressed in diopters. Magnifying power is not in diopters. It is the number of times the image gets magnified. It's just a pure ratio. If an object looks or subtends 2 degrees, maybe after magnification it becomes 10 degrees. It's subtending more angle. So 10 by 2, 5 times. So it is 5x magnification. That's what magnifying power is. That magnifying power is d by f if it is normal vision, and it is 1 plus d by f if it is at least distance of distant vision. If you are wondering what this d is, that is roughly usually 25 centimeters. That is your least distance of distant vision. For every human eye, that's the smallest distance till which you can see things clearly. Beyond that, you can see obviously. Before that, if you bring the object, it is a strain on the eye. Normal vision means the image is formed very, very far away. And least distance of distant vision means it is formed very, very close. This is more, this is less. So obviously when the image is far, the magnification won't be much. When you bring it close, then the magnification will increase. So that's how you get these two formulas. Then talking more about optical instruments, one second. Yes. So for compound microscope, the microscope which you use in your laboratory, then the magnifying power is a product of two numbers, please mind it, is the magnification of eyepiece multiplied by, because the eyepiece actually acts like the magnification of, not the eyepiece, my bad, magnification of the objective lens, means the lens which is closer to the object, multiplied by the magnifying power of eyepiece. Remember, the eyepiece is the one which acts like the magnifying glass, what we studied just before. So magnifying glass formula we already know, so that's why this number over here will be either d by f or 1 plus d by f. This is for normal vision. What is this? Dolby vision? No, this is for least distance of distinct vision. Very good. Free chapters. Karthik will get it live very soon. Don't worry about it. Okay. Yes. And over here, magnification is always image distance by object distance. So from the objective, that's why I'll put VO and UO. Usually, very important, usually it so happens VO is almost the length of the microscope and the object distance is almost close to the focal length of the objective, usually. Okay, if it is not, then you will substitute or find it like a normal lens problem. Keep this in mind. Okay, then the next one is for your telescope. Telescope is the simplest one. Telescope is the simplest formula. Actually, many problems usually come from telescope. The magnifying power is nothing but FO by FE, that's all. And also FO plus FE is nothing but the length of the telescope. Is that okay? Length of the telescope means distance between objective and the eyepiece lenses. Ready guys for the last leg? Thermo little bit and modern physics. That's all that is remaining. Are you guys ready? Let me know in the chat box. Full Josh, full energy. Wow, such a nice lecture. Yeah, and look at this, all those students who are watching this lecture live or even recorded, you know, if you are going with the flow, I'm pretty sure you will be realizing so many things. You will realize that, okay, I have to study that, I have to study this. Oh yes, now I understood this formula. Okay, and now I will not forget this because I'm seeing sir do it. So that's the best part about this class, right? This is like the most effective class I feel just before your JEE Mains, JEE Advanced and even BITSAT and CUET. Make sure you have saved this video somewhere. That's why I like it. And when you like, what happens, at least YouTube knows that, okay, you like this video, suggestion will come accordingly. And if you forget where this video was, again, you can, search through your history by searching through the liked videos and all of that. So that is very, very important. Okay. Right, let's begin. Wow, Lingeshwaram is seeing it from the start. Nice, yeah, nice. Thank you. And Anungla, thank you for putting up all the warrior Pandus. Whistle Podu. Let's start now with the, where is it? Yeah, this one. Process relation. Okay, so we have come to thermodynamics, of course, like I can see. All right. By the way, my system has begun to hang. We are not hanging. You can see, some of you are very keen observers, might have seen that as I'm writing, it has become slow.
Computer is only taking a lot of time to process it because there are close to 104 pages of PDF. So it's storing it in its cache, or I don't know, RAM or something. Probably it's getting overloaded. So hopefully it does not crash. Maybe I should just save it on the safer side. You know, if it crashes, I will cry today then. I will just cry. Formula, let me just call it as formula. I'll just save it. I'm just very scared where it will crash. See, for saving only it is taking so much of time. Computer is taking so much of time. Okay, let's just wait meanwhile. Okay, please don't crash. Please don't embarrass me today. Wow, this has taken so much of time. Thank you. Saved successfully. Please smash the like button for that. It has saved. If you have smashed already, don't smash it again. It will again come back to normal. Okay, very good. Thank you so much. Thank you so much. Let's do this. Let's do this. What is it? Process relation, alpha, Q, this and all. So I'll explain you what I'm trying to do over here. Go back. Yes. Any process can be written down in the form of a polytropic process form. In thermodynamics, polytropic means pressure into volume raised to some number is a constant. By choosing this number, I can decide what type of process it is, and I will show you examples. Starting off with, let's say it is isothermal process. If it is isothermal, then the relation is PV is constant. PV is constant. That means PV raised to 1. PV raised to 1. That means alpha is how much? 1. So the value of alpha is basically 1. Next, if it is, okay, if it is isobaric process, if it is isobaric process, then the pressure is constant. Pressure is constant. That means volume by temperature is also going to be constant. Volume by temperature is also going to be constant, right? So the value of alpha will be, think about it. What will be the value of alpha? Pressure is constant. V raised to 0. V raised to 0 is 1. So pressure will be constant. So alpha should be basically 0. Alpha should be basically a big fat 0. Then we come to isochoric process. Isochoric process, my dear students. In that, volume will be constant, and it so happens using gas law, pressure by temperature will be a constant. In such a case, the value of alpha, believe me, comes out to be as infinity. You can try it out for yourself why it should be infinity. Okay? There is a small trick in that. You figure it out by yourself. Lastly, you have what is it? What else is remaining? Adiabatic process. Adiabatic process. In that, you have pressure into volume raised to gamma is constant. Also, you have PV raised to gamma minus 1 is a constant, right? That's what it is. And that means the value of alpha will just be simply gamma. Now, let's write down heat in each process. The formula for heat. The formula for heat will be for isothermal, okay, I'm not so sure, but maybe I can fill it later on. I think we'll fill isobaric and isochoric first. It's very simple. Isochoric, it will be NCV delta T, specific heat capacity at constant volume into moles into change in temperature. If you are talking about isobaric, that specific heat capacity will be at constant pressure. So that into delta T. Okay. Adiabatic, oh, that's simple. The value of heat should be 0 because no heat is exchanged from the surroundings. Can you see that? Yes, Indira, even any student, BITSAT, CUET, any student can watch it because the physics is going to be similar. Delta U is the very interesting thing. Whether it is isobaric, isochoric or adiabatic, for all the processes, it is NCV delta T. NCV delta T. It is nothing but NCV delta T. It is going to be the same. It's just going to be the same. And I hope you have not forgotten this. Q is equal to delta U plus W. Do you remember this? Delta U plus W. I hope you remember this. That was the first law of thermodynamics. Okay, I'll keep that in mind. What about isothermal? Why are we not filling it? In isothermal, temperature did not change. That means there was no change, only in the internal energy. There was no change, only in the internal energy. What about the work done? After integration, it comes out as nRT ln log of V2 by V1. Oh, so delta U plus work, 0 plus this will be this. So heat will be exactly equal to the work, which is nRT ln V2 by V1. It will be exactly equal to the work value, right? Here, if you want, you can add, subtract all these things, but there is already a formula for work for isobaric process. It is just going to be P delta V, which is also nR delta T. If you use Gass's law, it's one and the same thing. For isochoric, the best part is there is no work because there is no change, only in the volume. So no change in the volume, it is neither positive nor negative, it is 0. For adiabatic, if you notice, Q is 0. So delta U plus work must be 0. So work must be negative delta U. Work must be negative delta U. If you solve this delta U value, which is going to be minus NCV delta T, let me just write it little smaller, minus delta U, which is minus NCV delta T, and you substitute the value of CV also, which is R upon gamma minus 1, then you will get it as NR delta T divided by 1 minus gamma. You can absorb that negative sign in the denominator. This is the formula that you get for adiabatic. Now, what is that last column? It is specific heat capacity. For isobaric process, it is basically going to be Cp. It is just going to be Cp. For isochoric process, it is just going to be Cv. What about isothermal? Let's try to think. For isothermal, if I write Q is equal to nCt delta T, notice there is no change, only in the temperature, because temperature was a constant. Temperature was a constant. So delta T is 0. If delta T is 0, what will be C? What will be Ct? Ct will be Q by 0. That means not even a number. That means it is not even defined. It is not even defined. One second. Yes. I just put it over here. This value of Ct is not defined because anything by 0 is not even a number. Not even defined. Not even defined. Keep this in mind. Many people do not know this. If you talk about adiabatic process, Q is equal to nCa delta T. Remember, specific heat capacities are process dependent things. So depending on the process, things will change. Okay, observe this carefully. Because Q is 0, any number multiplied by 0 will be 0. Any number multiplied by 0 will be 0. Naturally, Ca should be 0. So specific heat capacity for adiabatic process will be a big fat 0. Keep this in mind. Is that okay, my dear warriors? Is this clear till this point? Okay, that was the table. Very, very useful. Now let's go to molecules, degrees of freedom and all these things. So if you talk about a molecule like helium, okay, which is monoatomic. So like helium, argon, these are monoatomic molecules. Then we will talk about diatomic molecules like oxygen, diatomic,
where you have one oxygen here and another oxygen over here. And even polyatomic linear, or I can also call it triatomic linear molecules, triatomic linear, like carbon dioxide. You have oxygen, then you have carbon, and then oxygen. They are all along the same line. The bond angles are 180 degrees. And lastly, you have in general some polyatomic molecule which is non-linear. So like H2O. So 2 hydrogens, 1 oxygen as it is. Bond angle is close to 108 degrees, not 180 degrees. In each one of them, what are the degrees of freedom? Let's talk about it. There are 3 translation, 0 rotation. So the total is basically 5. The total, what did I say? The total is basically 3. The total is basically 3. Similarly, if you go for diatomic or triatomic linear, there are 3 translation, 2 rotation. Totally, it will become 5. Whether it is this or this, it is the same thing. Okay, don't get confused. For polyatomic non-linear, it has 3 translation, 3 rotation. Total is basically a big fat 6. Now, what about this gamma value? Gamma, which is the ratio of Cp by Cv, is also 1 plus 2 by F. 1 plus 2 by F, standard formula. Substitute the degrees of freedom, which is 3. Over here, you will get the value of gamma. You will get the value of gamma. The gamma value 1 plus 2 by 3 will come out to be 5 by 3 over here. If you do the calculation for this, it will come out to be 7 by 5, which is 1.4. Here it is 1.67. If you do the calculation for polyatomic, 1 plus 2 by 6, 1 plus 1 by 3, which is 4 by 3, which is 1.33. As the degrees of freedom increase, the gamma value decreases. As the degrees of freedom increase, the gamma value decreases, and as degrees of freedom become large, the value of gamma will tend towards 1. The Cp and Cv values will almost merge together. There will be no difference between the two. Keep this in mind. Cv value, the formula for Cv, you can write it as degrees of freedom into R by 2, or you can also write it as R upon gamma minus 1. Both are the values of Cv. In case of Cp, you can write Cp is equal to gamma R upon gamma minus 1. Gamma R upon gamma minus 1, right? This is also a formula. So keeping this in mind, for the first one, the value of Cv will be 3R by 2 because degrees of freedom is 3. Cp value will be nothing but 5R by 2. You can solve this and figure it out. Here it will be 5R by 2 for Cv value for dia or trilinear. This will be 7R by 2. This will be 7R by 2. For the last one, be careful. Degrees of freedom will be 6. 6 by 2 is 3. So this will be 3R and this will be 4R. That's all. The ratio is 4 by 3, 7 by 5, 5 by 3. 5 by 3, 7 by 5, 4 by 3. Yes, perfectly matching. This is how you love this table. Very important. It's useful for solving these problems. More laws coming up on your screen. Gas laws and KTG. Pressure into volume is nRT. Everybody knows this. Pressure into volume is nRT. The value of R is 8.3. You know, this is joules per mole Kelvin. This is usually the unit which you will be using, not the liter ATM. It's useful in chemistry. The number of moles is the number of molecules by the Avogadro number. This Avogadro number is 6 into 10 to the power 23. This is number of molecules. You also sometimes might need something called as small m, which is the mass of a molecule, which is the mass of a molecule or an atom in a gas or a liquid. So that is the molecular weight divided by the Avogadro number. This is your molecular weight by your Avogadro number is the mass of a molecule. You will sometimes need it. You can also write PV's NRT in a different form like this. PM is equal to rho RT. This capital M stands for molecular weight. Please remember that. And obviously this rho stands for density. Many times you might have to use this relationship. Next important formula which you might be needing with respect to kTg. With respect to kTg, right? Let's have a look. One of the formulas is pressure into volume is 1/3 number of molecules into small m into VRMS square. Very important formula. PV is equal to 1/3 NMV square. N is number of molecules. Small m is mass of a molecule into root mean square speed. Then comes the speed formulas. The root mean square speed comes out to be root of, you can rearrange and get this, root of 3 RT by M. In general, this is nothing but root mean square. Means first you square it. Each molecule will have some speed, V1 square, V2 square. So you square each speed. Divide it by N. That means you take the mean. First square, then mean, then the root. Read it reverse. RMS, SMR. Read it as SMR. Square, then mean, then root. That's what you need to do. Then you also have average speed, which is root of 8 times RT by M. 8 times RT by M. Average means it is simple average, V1 plus V2 plus Vn, last molecule, divided by the number of molecules. And then you also get something called as the most probable speed from the Maxwell speed distribution curve. The number of molecules versus the speed graph in general looks something like this. Meaning there are certain number of molecules which are maximum in number at a particular speed. This is the most probable speed of most of the molecules, because some molecules are really fast, some molecules are very slow. So that's how you get the most probable speed, VMP, which is just root of 2 times RT by M. Everywhere RT by M is there, only the number changes. 3, oh sorry, I forgot that pi. 8 by pi and 2. That's your root mean square, average and most probable speed. Then you also have the formula for mean free path, lambda, which is also called as the average distance between successive collisions. Mean free path, that is given by volume divided by root 2 times pi, and you have d square over here and the number of molecules. Very important formula. You can get questions on that as well, where sometimes they might ask you time between the collision. You know this is the average distance. You know this is the average speed. Time is distance by speed. Time is distance by speed. That's it. That's how you get the time between the collisions of molecules. Those questions have also come in JEE Mains. Okay? That's how you do it. Okay. Thermal physics, we have done it in the first half. I'm not doing it again over here. So I'm just deleting this slide because we have done thermal expansion and all of this. Oops, why did I make a duplicate of it? Not needed, not needed. Okay, we have done this in the starting half. Okay, so I'm deleting that slide. Cool. Let's get on to modern physics. Comparing light, photon and matter and mass and matter wave, sorry. Now we know that light is a wave as well as a particle. It shows dual behavior. So imagine this is light which is traveling at speed c. There is some wavelength and yes, there is some frequency. The particle nature of the light is called as a photon. The particle nature of the light is called as a photon. Photon also travels with speed c. Mass of the photon is assumed as 0. Please remember that.
Please assume, remember that mass of the photon is assumed as 0 because of relativity effects. Don't worry about it. Just remember it is 0. That's all. And this light is an electromagnetic wave. Light is an electromagnetic wave. Electromagnetic wave. Matter, mass. If you take a particle having certain mass, I'm not saying mass is 0, some mass particle, if it is thrown with some speed, it can be any speed, 1 meter per second, 10 meters per second, 1 lakh kilometers per second. I have the choice. But in case of light particle, I do not have the choice. No matter what you do, it will move with speed c. The choice is not there with light. That choice is there with mass, with matter, with electron, with proton. Keep that in mind. That matter also has a wave associated with it that has again some wavelength. It has some frequency. It will be moving with some speed, right? That is called as the matter wave. It is not electric. It is not gravitational. It is not magnetic. It is not nuclear. It is a different kind of wave. You cannot see it. You cannot feel it. But experiments suggest there is a matter wave. There are multiple experiments to prove that. Okay, don't worry about those experiments. Some of the experiments are single photon experiments. Then seeing light, seeing an electron in a YDAC setup, exhibiting YDAC kind of behavior when light is turned on and when light is turned off. Those are some complex, but you can also see some videos, and you can see some simple videos which will make you understand what it means. But right now it is not needed. Just before the exam, don't waste your time there. Come back over here. Now, in case of light, the momentum of the photon, even if the mass is 0, the momentum, okay, the momentum P is given by h by lambda. Please do not use mass into velocity. That will be stupidity. Don't use that. Next, in case of particle, the momentum is just given by mass into velocity. Yes, you can use that. There is no harm in that. You can definitely use it for a normal particle, but not for light, because mass only is 0. Please don't use that. Next, if you talk about kinetic energy of the particle, that is given by half mv square. I can also call it as the energy of the particle. Which is half mv square, which is kinetic in nature. Here, that energy is neither kinetic nor potential. It's just the energy of the particle. It's just the energy. Do not call it kinetic. Do not call it potential. It's just the energy. And that is hf, which is also hc by lambda, because we know that this is true. C is lambda into f. Right? So that's why f can be written down as c by lambda. That's what you can do. That's the energy of a photon. Whatever I'm writing in orange is particle behavior. Whatever I'm writing in yellow is the wave behavior. Please mind that. Okay. Please do not write energy as here half mv square. If you write it wrong, that is wrong. It is invalid. You cannot write energy for a mass as hf. No, you cannot write it. That is invalid. Now, what de Broglie thought was, since momentum is h by lambda, so he thought, can I write lambda in this case of a matter wave is h by p, and it came out to be perfectly correct, and even experiment suggested that this equation holds true. This is wavelength not of the particle but of the matter wave. Many people think the particle goes like this, up and down like that. No, it is the wavelength of the matter wave over there, which is h by p, my dear students, by just flipping the terms. Very, very interesting.
Very, very interesting. This part has the wave behavior, this part has the particle behavior. So this equation relates wave behavior with particle behavior, which was given by de Broglie. This is also called as the de Broglie wavelength. This is also called as the de Broglie wavelength. Is that clear, my dear students? Everybody with me? Very good. So, shall we go ahead? Shall we go ahead? Yes. And in case you are not aware of these concepts, please watch my lectures which are there on the channel. I have explained this in Modern Physics Flash series, which was conducted recently. If you can't find it, it's simple. Go to YouTube search. Go to YouTube search, search for Shreyas Sir Modern Physics. You will get many videos. Shreyas Sir KTG. You will get the video. Shreyas Sir Units and Dimensions. You will get the video. Always search for Shreyas Sir topic name. Physics topics only. Don't search for chemistry and maths. Okay? Fine. Alright. Sheetal, I think you should do that. Yep. Right. Okay. So that was about light, photon, mass, matter, wave, all these things. This is done. Now, photoelectric effect, standard things which you must know. If light is incident of frequency f more than the threshold frequency, then photoelectric effect occurs and you will see electrons coming out at different speeds. Some will be more, some will be less. The maximum will be Vmax. Any material will have its own property called as the work function, which is the minimum work function, which is the minimum energy to knock out an electron. This is standard. The equation looks something like this. The energy of the photon, which is also hf, will be equal to work function, minimum energy to knock it out. That is also given as hf naught. F naught is the threshold frequency. And then on the right hand side, you also put your maximum kinetic energy, which is also half m Vmax square. It's one and the same thing. Half m Vmax square. If you can measure this kinetic energy by a stopping potential, it will be E times of Vs. This is your stopping potential. Keep this in mind. So the energy which is given by the photon is used to knock it out first, and the remaining is there as the kinetic energy. That's all. It's a simple energy equation. Even if you do not know photoelectric effect, you can normally think, oh, the photon's energy came, some energy it took to bring it out, and whatever was remaining is there as kinetic. And that kinetic energy can be stopped by applying a reverse voltage. So when you decelerate the electron, it stops. So that electron charge into Vs is basically your stopping potential. Keep this in mind. Oh, there was one more thing which I wanted to also give you over here, specifically here. This energy can also be written down as 1240 by lambda. If this is in nanometers, then use 1240. The answer you will get is in electron volt. If it is in Armstrong, then 12400, provided the wavelength is in Armstrongs. That answer will be also in electron volts. So one more zero if it is in Armstrong, if it is not, then 1240 by lambda in nanometers, simplifying the calculations. That's all. Okay. Apart from this, you also will see that there are certain graphs which are very important in photoelectric effect. Every time they will ask you, this is current versus intensity graph. The current versus intensity graph is just a simple straight line. Basically, current is directly proportional to the intensity. More the photons, more the intensity, more the current, because more photons will take out more electrons. More electrons means more current will be there in the circuit. That's one of the graphs. Another graph which is very important is this graph of voltage versus the current, and that graph looks something like this. This is for intensity I1, this is for higher intensity. This point where it converges is the stopping potential. I put it minus because it's on the negative side, otherwise it's just converging at the same point. So as the voltage increases, the current increases and saturates. But if you reverse the voltage, current will reduce and become zero. This is where the current becomes zero. That's why it is called stopping potential. Another graph which is very, very important for all of you is this one, where you show it for different metals or different surfaces, where you will see that the slope is the same, h by e, for different things, where I think on the x-axis and y-axis you have frequency and I think voltage or something. I think it is voltage, stopping voltage versus frequency. So that's what you will get. The slope is constant and for all of them. Okay, just check this out. I will not put it over here. I don't remember it right now, but yeah, just check that graph out. Okay, later on. The slope is the same. If the material changes, then you will see the y-intercept is different. Just check that graph out. It is also a very important graph. Okay, cool. Chalo, that was photoelectric effect, my dear students. Let's move on to the next one, atomic structure. Standard things which you must know in atomic structure. Bohr's postulate, yes. The angular momentum is nh by 2 pi, number one thing. N is the principal quantum number. This is your principal quantum number. H is Planck's constant, standard. Next thing which you should also know is that if you take any orbit and you know the de Broglie wavelength of the electron, you will see n times the same n times lambda is 2 pi into the radius of the orbit. 2 pi into radius of the orbit means the circumference. The circumference exactly has n times the de Broglie wavelength. This lambda is the de Broglie wavelength of the electron in that orbit. Remember de Broglie wavelength? I had explained it to you right over here. De Broglie wavelength. Okay, this is the wavelength of the matter wave. This was given by de Broglie. Right. Cool. So moving ahead over here, standard formulas which you must know again. Radius is 0.529 n square by z Armstrong. Radius is proportional to n square and inversely proportional to z, standard thing. Then velocity is proportional to z by n, and energy is minus 13.6 z square by n square electron volt. Z square by n square electron volt. Keep this in mind that this energy is the sum of kinetic plus potential, and the kinetic energy is negative of the total energy. Just one second. And the potential energy is also going to be 2 times of total energy. This is also a very important formula. Many times they will just ask you kinetic energy or potential energy. So from this you can reverse calculate it. Very standard thing. Also bear this in mind, as any electron moves in a circular orbit, there will be a force of electrostatics, and that electrostatic force is responsible for mass into centripetal acceleration. The centripetal acceleration only is v square by r, and this electrostatic force is 1 by 4 pi epsilon naught. Here you will have the charge on the nucleus, which is Ze, into charge of the electron upon r square. In fact, using this and this only, you get these formulas. Okay, all these are derived using these basic principles. Cool, my dear warriors. Very good. Then you have electron transitions from high to low, low to high, and all these things. So one thing you must be very, very clear. Let me just make a duplicate. So if an electron gets excited and if this electron jumps to a higher orbit, that is being called, it has got excited, then it needs energy to go to a higher energy. So what will happen? It will basically absorb a photon. What will it do? Absorb a photon. And the reverse is also true. If it is already excited and now it gets basically de-excited, then in this process, what it will do? It will basically emit a photon. In this process, whether it goes here or there is some energy transfer which is happening. So the difference of the energy in the orbits is exactly the energy of a photon, and never will you see for a jump 2 photons are emitted. For one jump, 1 photon. For one jump, 1 photon. Always remember that. So this is always going to be hc by lambda. This will be also E2 minus E1, whichever is bigger, you put it first. After solving, here is what you get. 1 by lambda is a constant into z square, 1 by n1 square minus 1 by n2 square. This is your Rydberg's constant, almost 1 into 10 to the power minus 7, right? So that is the standard value which you should remember, and this formula is useful for finding the wavelength. That formula is useful for finding the wavelength of the photon which is emitted or which is absorbed. Keep this in mind. Sometimes during the de-excitation process from higher energy level to a lower energy level, let's say electron is here, it gets de-excited. There are number of ways in which it can get de-excited. Maybe step by step, maybe in one go, maybe it went here, then it went here, okay, or then it went here like this, or maybe it first got de-excited from here, then it went here. So there are permutations, combinations which you can do. So the number of wavelengths from an excited state of n which are emitted is given by, the number of wavelengths is given by nc2, basically n into n minus 1 divided by 2. This also has come many times in the examination. Okay, clearo? Shall we go ahead? Very nice. So you should know all these things, guys. Lyman series, Balmer series, Paschen, bracket and P-fund. Please take a screenshot. If any line comes from high to 1, it is Lyman, then Balmer for 2, Paschen for 3, bracket for 4, P-fund. Generally Lyman, Balmer, Paschen only maximum questions will come. You should know these energy values: minus 13.6, minus 3.4, minus 1.5, minus 0.85. These 4 values at least you should by heart for hydrogen. From that you can easily calculate for helium or lithium and all these things. Okay, this diagram should be there in your head. This diagram should be in your head. You should also know whose wavelength will be more, whose wavelength is less. Think this way. Over here, energy difference is hc by lambda. So the one which has larger energy difference will have smaller wavelength. So this large line will actually have small wavelength. This small line, small energy, will actually have large wavelength. Same thing for Balmer also. Please understand, for large energy difference you will have small wavelength. For small energy difference you will have large wavelength. So these things are also useful in many problems. They might ask you the ratio of maximum to minimum wavelength.
and all those things. Sometimes the first line of Balmer to first line of Lyman, all these things. Smallest line of Lyman series is, smallest line means, smallest wavelength means from infinity to 1. All these are standard questions. Okay. One more thing, they can also ask you ionization energy. They can also ask you ionization energy. So ionization energy will be just 13.6 Z square by N square electron volt. Ionization energy means to take that electron from the ground state to infinity, from the ground state to infinity. That energy is called as ionization energy. Keep that in mind. That is also useful. It's just negative of the energy of the electron in that orbit, right? Standard thing. Okay. Then nucleus. Let's talk about nucleus. Okay. So, yeah, in nucleus, what are the basic things that you must know? First of all, you must know, let me just make a duplicate of this. Yeah, atomic mass, oops, see this. Okay, atomic mass, atomic mass number is Z plus N. This Z is number of protons inside a nucleus. This N is the number of neutrons inside the nucleus. This is the atomic mass number of the nucleus. The nucleus has a size, has a volume, has a radius. The radius of the nucleus is proportional to atomic mass number raised to 1 by 3. Atomic mass number raised to 1 by 3. Keep this in mind. And if you try to find the density, which is the mass upon the volume, if you do the calculation, it comes out to be constant for all nucleus. For all nucleus, it comes out to be a constant. Keep this in mind. Okay, this is with regards to the basic nucleus properties which you must know. The protons and the neutrons, the proton, neutron, proton, or neutron, how are they together? How are these together? It's not because of electric force, it's because of the nuclear forces in between them. These nuclear forces are very different. They depend on the spin. They don't depend on the charge. They don't depend on the charge. They don't depend on the charge. They are very powerful. They are very strong. They are very strong, and they are very short distance. Only acts for a short distance, typically of the order of femtometers. This F, you will see that F is basically 10 to the power minus 15, femto, Fermi, whatever you want to call it. This is with regards to that nuclear force. Then what happens is whenever you form a nucleus, you take protons and neutrons and bind them together. So there is some binding energy which is released. So if you take protons, how many protons you took? Z number of protons you took, and you added neutrons. Neutrons don't have any charge, so N number of neutrons, and you bind them together, you will get basically the nucleus. You will get the nucleus, and in this process you will see a binding energy is basically released. That binding energy calculation can be found by the mass defect. The total mass here and this mass is not the same. So that is called as the mass defect. And that mass defect delta M comes out to be, usually this mass is higher, this mass is less. So it's the mass of the protons, of each proton into Z, plus mass of each neutron into
basically number of neutrons into number of neutrons. This is the total mass on the left hand side. Subtract it with the mass of the nucleus. Subtract it with the mass of the nucleus. That is your mass defect. Now usually these masses are calculated in something called as AMU. You should know this. 1 AMU is nothing but 1/12 the weight of the 1/12 the mass of the carbon 12 isotope. It's very small. It's 1 point something like 65 10 to the power minus 27 kg. It's very small. And mass of the proton is almost the same as mass of the neutron, which is very close to 1 AMU. So like 5th, 6th decimal or 4th decimal the changes happen, but otherwise they are very close to 1 AMU, because there are 12 number of nuclear particles in a carbon atom. So if you divide it into 12 parts, each part will be almost the mass of a proton or a neutron. Proton and neutron are almost the same mass. Keep this in mind. So having said that, you will get the binding energy by this formula. The binding energy is given by delta M into C square if you want it in SI units. Else you can write it as 931 into delta M, provided this is in atomic mass units only then, but this will be in mega electron volt. Mega electron volt. Keep this in mind. Now you can also find something called as binding energy per nucleon. This is binding energy per nucleon, and you can draw a graph of that versus different atoms. Binding energy per nucleon, that means per nuclear particle. That graph comes out to be somewhat like this. It is maximum for iron, and this actually tells me the stability of the nucleus. Stability of the nucleus. Keep this in mind. More the binding energy per nucleon, more stable it is. So the most stable is the iron nucleus. Anything on this side or this side is less stable than iron. So the elements of higher order, which are very heavy like uranium, thorium, they would want to come over here by breaking into small parts. That is called as fission. Whereas the elements of smaller atomic number, they want to reach here by combining together by a process of joining, which is called as fusion. Keep this in mind. And any nuclear reaction doesn't matter. Okay, maybe there is a nucleus like this. It disintegrates into Y, and some alpha or beta or gamma particles come. So this is called as the parent. This is called as the daughter, right? Sometimes they might combine. Whatever happens, there will be some energy which is released. That is called as the Q value of the reaction. That Q value of the reaction is basically just like this binding energy, guys. Just like this binding energy. So that Q value of that fusion or fission reaction is the defect of the mass. That means the difference of the masses into C square. If you want, you can write it as 931 into delta M, provided it is in atomic mass unit, mega electron volt. Keep this in mind. That is the Q value of the reaction. Cool? Great. Last few things coming up on your screen regarding current. There are certain things, because I need it for semiconductors. Current, which is dq by dt. I can divide that current with area of cross section which is flowing. I will get current density. And
you need to continue in the app.
Oh my god. So that's my phone. Okay, so current density. Then when you pass that current, these electrons are moving in the exact opposite direction of the current. So there is something called as the drift velocity. So the formula for drift speed is given by current is equal to NVDR. This drift speed is this VD. This is the charge per unit volume. How much is the charge carriers? How much is the charge carriers per unit volume? This N will be generally given to you. E is 1.6 10 to the power minus 19. A is the area, I is the current, V is the drift speed. Very easy to remember. NVIDIA graphics card company. Current is NVIDIA graphics card. That's all. Next few things which you should know. What is it? Just like V is equal to IR, instead of voltage, you can use the electric field which is inside the conductor, because obviously if the electrons are moving, there must be some electric field. This is positive, this is negative, high voltage, low voltage. So there will be an electric field inside the conductor because there is a voltage difference. So instead of voltage, you can use electric field. Instead of current, you can use current density. Instead of resistance, you can use rho. Rho is resistivity. Remember, rho L by resistivity. Some people also like to write it as, bring it on the other side, 1 by rho into E into J. This is sigma E is equal to J. What is this? This is conductivity. This is conductivity. What is this? This is resistivity. This is resistivity. Also, there is one more formula for drift speed which you must be aware of, and that is the drift speed is nothing but E into electric field, charge into field, divided by mass into T. This is your relaxation time. Relaxation time, something which you should be again aware of. Relaxation time. Keep this in mind. So if you know drift speed, you can find relaxation time. If you know relaxation time, you can find the drift speed. Standard formulas. You should also know something called as the mobility. Mobility is given by mu, which is the drift speed per unit electric field. Drift speed per unit electric field. Okay, standard formulas. All these are current parameters which you should know. Also, one more thing, this sigma, which is conductivity, comes out as your mobility into the number of charge carriers, which is N, into basically your E. Yes, mu NE. Yeah, that's what you will get it as in general. Also keep this in mind, something which you should be careful, that as temperature increases, resistivity also increases, conductivity decreases. Conductivity will go down. When the resistance is more, temperature is also more. More temperature, more collisions, more difficult for the electrons to move inside the conductor. These are current parameters. Now, in semiconductors, which have a small band gap energy, because in insulators, the electrons find it very difficult to go from the valence band to the conduction band. In conductor, they are almost overlapping, so they can easily transmit to the conduction band and they can easily conduct. In semiconductor, a small gap is there, which is easily accomplished by temperature, by thermal collisions. So that's the reason why you will see in semiconductors, as temperature increases, resistivity decreases or conductivity increases. That's what happens in semiconductors. It's exactly opposite in conductors. So in conductors, as the temperature increases, resistivity increases, conductivity decreases. One more thing in conductors is that voltage is directly proportional to the current, but here voltage by current is not going to be constant for semiconductors. Is not going to be constant for semiconductors. Then you get two types of semiconductors. One is P type and N type, and you have semiconductors which are basically intrinsic, and then extrinsic semiconductors. One is P type, one is N type. In intrinsic semiconductors, the number of holes is the number of electrons, which is also called as Ni, intrinsic concentration. Here in P type, number of holes is more than number of electrons. In N type, number of electrons is more than the number of holes concentration. But in either case, in extrinsic, you can use this formula. Number of holes into number of electrons is intrinsic concentration square. Intrinsic concentration square. Keep this in mind. Cool? Now, in case of a conductor, what happened? The conductivity was because of electrons. Conductivity was because of electrons. So, in case of conductors, the conductivity is due to electrons. But in semiconductors, the conductivity is due to electrons and holes, both. So you will see that the conductivity formula is conductivity due to electrons plus conductivity due to holes. So use that formula, mu Ne, mobility into number of charge carriers into E. So it will be nothing but mu of electrons, mobility of electrons into number of electron carriers into E, plus mobility of holes into number of holes into E. So you can use this to find the total conductivity for semiconductors. This is for semiconductors. For conductors, remember, it is only this much, only because of electrons. So sometimes they can trick you into semiconductors and conductors like differences. Specifically in board exam, they can ask you to name the differences, but in JEE or other exams, they might play around with this. They might just play around with this. Okay, cool, great. So you should know the IV graph, current versus voltage graph, forward voltage, knee voltage, breakdown voltage, leakage current, forward bias, reverse bias. Please go through this graph. I have put it for all of you. 100% they will ask you questions. Also learn about LED, photodiode, Zener diode. 100% they will ask. And rectification you should go through. And yes, your solar cell. So go through all these applications and rectification process, just have a look at it. Okay, so these terms, what is the meaning of diffusion current, drift current, all those terminologies, please go through it. It is all theory. Okay, so diffusion current, drift current, diffusion, drift, all these things, please go through it. Cool? Yeah. Last thing in semiconductors, where is it? Logic gates. So I'll just show you all the operations for OR and everything. Just okay. So logic gates, starting off with, if you have this thing over here, it looks like a D, right? It looks like a D. A, N, and what is that? Is it looking like a D? That's it, AND gate. So this is AND operation. Then if you have this gate, okay, what you can do is make it look like this. OR, don't you see it is OR operation, right? And then if you have a gate like this, do you see that circle over there? That circle is basically a knot. That circle is basically a knot. Very good, very good. Similarly, you have other gates also, like this one. You have the D but a circle. This is NAND gate, and this one is oops, this one, or with a circle, that is NOR gate. Standard things which you should know. You should know the truth tables for each and every single of them. So 0, 0, 0, 1, 1, 0, 1, 1. And means both should be true. Only then it will be true. Only then it will be true. So I'll just put it over here for your sake. 0, 0, 0, 1, 1, 0, 1, 1. Right? So both should be true, then it is true. Else it is going to be 0. Or means one of them at least should be true, then only it is true. Not means, oh, sorry, here we don't need to. You can just do it, two things. Yeah, if it is 0, then it will give 1. If it is 1, it will give 0. Right? That's all. The AND operation is also represented with a dot. So it is represented as A dot B. A dot B. That is the AND operation. OR operation is represented with a plus. A, why did I put A bar dot B bar? Sorry. It is A dot B. Sorry. And this is nothing but plus A plus B. And NOT is represented with a bar. NOT is represented with a bar. These are the inputs. This is A, this is B. This is A, this is B. This is A. What you get is A bar. In case of NAND, if this is A, this is B, you are doing A dot B, and then you are negating it. In case of NOR, what are you doing? This is A, this is B. You are doing OR first. You are doing OR first and then negating it. Now there is a De Morgan's principle which can be used in many places like this. If it is A dot B bar, the dot can be made as plus. You write A and B separately, and then you also put the bar separately. So A dot B bar is A bar plus B bar. Very simple thing. Not just that. If it is A plus B whole bar, replace the plus with a dot, write A and B separately, put the bar also separately. These laws you can use it. These laws you can use it. They are called as De Morgan's laws. Very, very important. Also keep this in mind that if you short the terminals of a NAND gate, or basically you short the terminals, short means you connect them together, that's all, of a NOR gate, it is the same as a NOT gate. So these are all equal. These are all equal. NAND shorted, NOR shorted, or not. All of them, they behave like a NOT gate. This can be used in simplifying many circuits. Yes, keep this in mind. Okay, clear? These logical operations, everybody with me? All right, just one second. Now, there is one more thing which I need to give. 1 second. I can go back. I can probably give it where I have given gravitation, escape speed, satellite speed formulas. I wanted to give that also. Okay, just put it over here. This is not needed anymore. Let me just delete it. So yeah, so in gravity specifically, yes, okay, so with regards to gravitation specially, there are some special formulas which you must be aware of. One thing is gravity on the surface. Gravity on the surface is given by G, gravitational constant, mass of the planet divided by r square. Gravity at depth d, this is at depth, is given by gravity on the surface, 1 minus d by r. This formula you can use. You can also use this gm small r divided by r cube. This is the distance from the center. This is distance from the center of the earth. That also formula you can use. When it is gravity at height h, you can use this formula, gm divided by, instead of r, it is r plus h whole square. You can use that, or this is for any height, or you can use this approximate formula, g, very similar to this, 1 minus h by r, only if h is much smaller than r. Otherwise, do not use this approximate formula. This is only valid in this case. And you should also know how the gravity changes with distance from the center. First it increases linearly, then it drops down. You will see that it is maximum on the surface. Keep this in mind. Also know the rotational effect of Earth. The gravity due to rotation will be given by g naught minus omega square radius of the Earth into cos square lambda. This is latitude of that place. Lambda is 0 for equator. If you go to the pole, it is 90 degree. For south pole, it is minus 90 degree. These are standard formulas. Then what else you have in gravitation? Satellites and Kepler's law. So in gravitation you have satellites and Kepler's laws. Those formulas are also very important. And escape speed formula. The speed to escape is given by root of 2gm by r. And if the escape speed is more than or equal to speed of light, then it becomes a black hole. Keep this in mind. If you have a satellite of small mass m doing an orbit of radius r with some velocity v around another massive planet of mass m, then this orbital speed is given by root of, instead of 2, it is just g m by small r. This is the speed of the orbit. So orbital speed. You also have the formula for the time period, which is 2 pi root r cube by gm. That's the formula for the time period. Also you have the formula for energy, which is minus g capital M small m divided by 2r. And also keep this in mind that this energy which is there, you can relate it to kinetic energy like this, just like in atomic structure. It is negative of kinetic energy is negative of total energy, and potential energy is twice of the total energy. So these two things are still valid even in gravitation. Also remember Kepler's laws, everyone. You have a massive object at the center of which the other thing is revolving. That is always going to be at the focus, and your small satellite or the planet of mass m is going to revolve like this in an elliptical orbit. Keep this in mind. This point, when you are the closest, r1, over here, you will have maximum speed, and this point, when you are the farthest, you will see your speed will be the least. In fact, you can also write this. Let me put mass on both sides. M, mass of the planet, into R1 into V max is equal to M into R2 into V min. Why can I do that? Is because this is actually angular momentum, and that angular momentum is conserved. The angular momentum is conserved about the sun, about that massive object. Angular momentum is conserved. MRV is the angular momentum formula. Also, there is a thing for the area swept. If this is the area which is swept, so that dA by dt, which is also called as the aerial velocity, that is nothing but L by 2m. Angular momentum is constant, mass is constant, 2 is also constant, that is constant. So it sweeps equal areas in equal intervals of time. That is your second law of Kepler. And the last law is seen even here also. The last law is even seen here also. You can see if you square it, T square is proportional to R cube. So T square is proportional to R cube is your third law of Kepler. Is your third law of Kepler. Right?
Well, my dear warriors, I hope you enjoyed this session by your Captain Shreyas. If you're wondering where you can get the PDF of this particular session, well, the link is there in the description box. Make sure you check it out. And also join the Telegram channel in case you have not joined that yet, so that you get all the latest updates, right? And if you're also looking for the full syllabus mock test series, absolutely free of cost, that link is also there in the description box. So God bless you all. Thank you for liking, and do not forget to subscribe in case you haven't. This was your Captain Shreyas signing off. Hasta la vista.